So can we start now?
Yeah, let's start.
Okay. So good morning, all. So we welcome you all for the day 2 session for the joint FDP. So today in the day 1 session, day 2 session first lecture is being delivered by Dr. Sudarshan Mukherjee from IIT Guwahati. Dr. Sudarshan Mukherjee received the BTech degree in Electronics and Communication Engineering from NIT Durgapur in 2011, the MTech degree in Electronics and Communication Engineering from IIT Roorkee in 2013, and the PhD degree from IIT Delhi in 2017. From 2017 to 2019, he was a postdoctoral researcher with the Department of Information and Communication Engineering in the Institute of Science and Technology, South Korea. Since January 2020, he has been an assistant professor with the in Electronics and Electrical Engineering Department of IIT Guwahati. His main research area include wireless communication, use of large antenna arrays, signal processing for wireless communication, mobile edge computing, and ultra-dense network. He has also served as a technical program committee member for several IEEE conferences and workshops. He is also currently serving as a reviewer of several IEEE journals, and he has recognized as a recognized reviewer of the IEEE Communication Letter in 2018. With this, we would like to welcome Sudarshan sir to please start the session.
Okay. Thank you. Good morning, everyone.
Thank you, sir.
Let us start. We have already been delayed a little bit. So let us start with our presentation today. So today, the topic that I'm going to talk about is optimal receiver design for AWGN channels. So far, we have been in previous day 1 we have been talked. You have talked about how the digital transmission system works and how the different signals they are represented in signal space form, so that they can be represented in a more basic manner that they can be understood, and how the transmissions and how the transmission scheme that will work and how will decode, and that will lead us to how we'll decode those information that are being received at the receiver. So the question that comes is, why do we need the receiver, or sorry, why do we need the receiver, or how do we design the receiver? As you can see, whenever we use the digital transmission system, it sends its information in the physical channel using a modulated carrier. Through this information transmission, it is being received at the receiving end, where we want to understand what information has been transmitted. So essentially, what we see that whatever we transmit from the transmitting end, be it a cellular, be it a cellular base station, or some other mobile device, or something else, the everything that we receive at the receiving end, it depends on the state of channel, and depending on this channel, it we decide how we are going to retrieve the information. So if we want to design a receiver, or if we want to retrieve some information that has already been transmitted from some source, we need to have some common guiding principle for design of those receivers or those devices that can help us understand or detect or decode the information that has been transmitted. These common information for receiver design or the detector design, whatever we call it, it's primarily based on decision theory and the detection estimation. And of course, we need to understand that any principle that we use for receiver design purposes must give us the best possible result that we can achieve, whether it is the best possible result we can achieve if we want to which essentially means that we need to minimize any kind of error in detection, or the detected or estimated information must be almost exactly a replica of that information that has been transmitted. So if we summarize, what we need is that the common guiding principle that has been based on a detection or decision theory, and we need to enable ourselves to have an optimality of the decision making. With this perspective, let me first introduce the outline of today's lecture. So today we'll first discuss a little bit on decision theory and optimality of detection. Then we'll introduce the waveform and vector AWG channel concepts. And once we are familiarized with the waveform and vector AWG channels and the decision theory and how optimal decision making works, or how detection can be made optimal in terms of error performance, we'll go into the optimal receiver structure. And in optimal receiver structure, we'll primarily concern ourselves with the correlation receivers and match filter receivers. And once we have understood all these things, we'll go and look for how the probability of error is defined and how the error performance can be computed or can be analyzed. So let us first see how decision making works. So as you can see, whenever we talk about decision making regarding something, we need to have a source from which which will generate some amount of information, and we need to have a receiver, or we need to have a receiving end where that information that is being transmitted from the source will be present or will be received. So if we look at the decision making process, or the diagram based representation that is being shown here, just give me a minute. Okay, I think it is not allowing me to. Okay, now that I have the pins. Okay, so if we look at this entire process of decision making, we'll see that there is a source from which the information is being transmitted. There is a observation space which essentially represents the received signal, and this received signal is being detected, or the decision making that is being made at the at the receiving end. So if we make this an analog, or if we make this an analogous to the actual digital communication system, we can view this source at the digital transmitter, which is actually transmitting different sets of messages. The probabilistic transition mechanism that alters the transmitted information is essentially the channel, and there in the observation space there is a received signal space. And the observation space or the received signal space is what actually we are receiving at the receiving end. And after that, we are based on this observation space, we are making some decision on what information that has been transmitted. So there are three distinctive parts that we see that the decision making process or the detection process has: the source, the set of which is essentially the set of all messages; the observation space, which is the set of received messages, or we can even say in case of digital communication system, it is the received signal space, and it has its own probabilistic distribution because of the influence of the channel. And finally, based on the source, we have some hypothesis or regarding what has been transmitted, which is the basis of our decision making. If we make it equivalent to a digital transmission, or one of the most basic form of digital transmissions, then we can view the entire source as the set of messages, which are binary messages consisting of zeros and ones. The observation space is obviously the received signal, which is received for the AWGN channel, and therefore will have a Gaussian distribution. And the hypothesis regarding the transmitted message will decide whether a 0 or 1 has been transmitted. If we go about this mathematically, then we can represent in the traditional using the traditional notation. Each hypothesis can be represented as hi, where I represents the index of the hypothesis. So hi represents the ith hypothesis, which actually corresponds to the ith message that is being transmitted, and the received signal R can therefore be given as a summation or of the transmitted message and the noise in the AWG channel. So uh, just so ultimately what we need ultimately what we see that in a binary decision making process, we have a detected message R. We understand the noise statistics based on the nature of the channel, or the distortion, or the amount of distortion or the influence the channel exerts from the statistics of the channel. And we understand that we have some source information that will also influence the received signal. So if we are to detect the message, if we are to detect the actual message that has been transmitted from this received signal space, or to want to make the best decision on the hypothesis, so what we need? It turns out that we need three things. First, we need to understand how the source works, or what type of message the source will transmit and when, which essentially boils down to the source probability distribution of the transmitted message. Second thing that we need to understand the distribution of the received signal based on the transmitted message and the channel. And the third thing that we need is a cost function which will oversee the fact that we are making some amount of decision based on the hypothesis and the distribution of the received signal that we have. This cost function will allow us to understand the extent of the impact of error in detection, and in turn will allow us to minimize the error in detection. So let us talk about in a general scenario where there are m messages that can be transmitted from the source, and at the receiving space there are m different types of messages can be housed in a large observation in a universal observation space. And if we see the entire process, then we see that the source message, it will have a distribution of the it will have a its distribution will influence the received signal, as well as the channel, as well as the influence of the channel that has to be there. So if we see um, this entire process, what we see that the source, it has some individual informations or individual information symbols that are transmitted at with a distinctive probability. And once this information has been received in the received space, each of them will occupy a distinctive region in the observation space. This particular form of partitioning of the observation space, depending on what type of information that has been transmitted, is called partitioning it in a decision region, which essentially means if we transmit the message m0, which corresponds to the hypothesis h0, any received signal that has been transmitted for that particular information will occupy the observation space, a subset of observation space z0. The same goes for the hypothesis h1, h2, and ultimately hypothesis hn-1. Now, the question comes is, how do we define or how do we design this observation space? These observation space that are being designed or that are being called into action are based on cost, or are based on the cost function that we are implementing to make the decision. So ultimately what we decide based on what message or hypothesis that has been transmitted, or ultimately whatever decision we make in favor of any hypothesis, it will minimize the error cost. Let us take up an example of binary hypothesis testing for the Bayesian cost experiment. Now, I have specifically chosen this binary hypothesis testing because it resembles the digital transmission system in the or it is in a very similar in a very intimate way. Like I said, in a most basic form of digital transmission system, there are two different sets of messages, 0 and 1. So we also have two different distinctive hypotheses here, H1A and H0. And for each of these hypotheses, we'll have a two distinctive regions in the observation space, Z0 and Z1. And of course, we assume that since we are talking about a generic Bayesian experiment for binary hypothesis testing, we assume that each of these messages have different transmission probabilities from the source. So for the message 0 or H0, the probability is P0, and for H1, the probability is P1. As you can see in this entire process, whenever the source transmits the message H1, it will occupy the decision space Z1. If it transmits Z0, H0, it will occupy the decision space Z0. And since it is a binary decision system or a binary hypothesis testing system, we also add a corresponding cost function which is binary in nature. Or we can say that the cost function that we are considering, it has a zero cost for making a correct decision, which is the most favorable for any kind which can be considered in the one of the most favorable situations and the most simplistic situation, of course. And we also consider the cost for any kind of incorrect decision on hypothesis as 1. This gives us a cost which is primarily based on the incorrect decisions. And as you can see, the cost function that we have presented here is a Bayesian cost function. This Bayesian cost function, it has two components. The first component is based on the incorrect decision that has been made for hypothesis H0, and the second component is for hypothesis H1. As you can see, the conditional distribution FR condition on H0, it essentially represents the distribution of the received signal conditioned on the fact that the hypothesis H0 is true, which means that information 0 has been transmitted, information index 0 has been transmitted, and therefore we multiply it with the corresponding probability P0. And as you can see, for incorrect decision, we integrate this distribution to generate the probability over the decision region Z1. Similarly, for the hypothesis H1, we integrate it over the decision region Z0 for incorrect decision and multiply with the symbol transmission probability P1. So this gives us the total received total cost function that we can incur when we are making a decision for the entire experiment. Now, if we look at the fact that we have some cost, we need to find a way to minimize this cost. The best possible way, or the most simple way to minimize this cost, is to turn one of these integrals negative, so that the negative term can dominate the positive term and the cost falls below to 0 or beyond that. For this purpose, I have modified this second option or the second term so that we can represent it in terms of the integral over the decision region Z1. And voila, what we see that we have a positive term P1 and difference of these two integral terms which are over the same decision space Z1. As you can see that P0 and P1, they are coming from the source, so they are essentially out of our hand. We cannot make any changes to them at the receiving end. So the only thing that we can see is that the only thing that we can modify is the decision region Z0 and Z1. And we can see that if we want to minimize this cost, we need to have this probability, this integral which is based on the hypothesis Z1, H1. It should exceed the integral, it should exceed this term P0 and P0 multiplied with the conditional distribution for H0 in every possible way. So ultimately the cost is minimized for this binary hypothesis testing if we are making a decision in favor of H1, hypothesis H1, if we have P1 multiplied with conditional distribution for H1 exceeds P0 multiplied with conditional distribution for H0. Now that we have understood that this particular how this particular binary hypothesis testing and the decision making process can be optimized, we can similarly extend this idea to the MNI hypothesis testing case, or in case of a generic M message symbol case, where if we want to make a decision in favor of message MI, which is essentially related to the hypothesis HI, we need to satisfy the condition that the joint probability, the joint distribution of the receive symbol and the source should, for the ith message, for the ith message, must exceed the joint distribution for all other messages. If we look at this, then we'll see that this is something very similar to, or we can say that it is exactly similar to what we normally call maximum a priori probability decision. With this basic understanding of the entire scenario, let us first introduce what map decision criteria is. So the first optimal decision criterion that we are going to talk about is the maximum a priori probability, or MAP decision, and it determines the probability of determines the transmission of a message, or it detects or makes the decision based on which message has been transmitted based on the receipt signal. So the important thing is that the probability of a source message that is being transmitted conditioned on the fact that we have what we have received. So the optimal decision for a map decision criterion is based on the argument that maximizes probability that MI conditioned on R. Now, using Bayes rule, we can simply convert it into what we have seen in the cost minimization criterion from our previous slide, which is essentially gives us the product gives us a ratio of the total distribution of the received signal and the joint distribution of the received signal and the ith information message. Now, as you can see that the total distribution of the received signal, it is essentially independent of any kind of particular message that has been transmitted from the source, and then the equivalent optimal decision obviously for the map is going to be represented by the probability of the ith message multiplied by the corresponding conditional distribution of the received signal. So as you can see, whether we are making a decision in favor of a binary hypothesis testing or a M-array hypothesis testing, or in general, if we are making a decision in favor of any kind of digital communication system, the best possible decision that we can make, or in order to detect the information that has been transmitted, it will be based on the map hypothesis criterion or the map detection. Now, so far we have been talking about the cases where all the messages have different probabilities at the source. That may not always be true if we are considering any practical kind of digital transmission scenario. For example, if we are transmitting a BPSK message symbol or a conventional QPSK message symbol, the most basic consideration is that the messages, they are all equivalent. or equiprobable. So if we extend this idea to the map decision criterion, where all the messages are unbiased, where the message source is unbiased towards any kind of message, then this idea directly reduces to the fact of email detection, which essentially means that we can simply ignore the source probability and focus on the fact what information that has been transmitted, and we can directly make a decision based on the distribution of the received signal, condition of the fact that a source message has been transmitted. So this essentially boils down. This essentially means that whichever message has the highest likelihood for the received signal, we make a decision in favor of that. That's why it is called the email detection. Now that we have understood, or we have gone through the entire decision making process and what type of optimal decision that we can make based on these processes, let us first talk about a little bit about the waveform and vector AWGN channel. And once we have gone through these waveform and vector AWGN channels, we'll see how do we make a decision, or in favor an optimal decision in case of a digital communication system. Now, the waveform channel or AWGN channel, it is essentially concerned with the continuous time waveform that is being transmitted. So the channel which is being corrected by the noise is essentially NWT here, is essentially a continuous time waveform of the noise, and we call it a AWGN channel because the first thing is that the noise is additive in nature, which means whatever information that is being whatever signal or with signal waveform that is being transmitted, you are simply adding the noise. It is white, which means that the noise power is uniformly spread throughout all frequencies, and it is Gaussian, which means that the random noise is Gaussian distributed. So the received signal model for any transmission time period 0 to t over which the actual information is being transmitted can be simply represented by RT, which is summation over MIT plus NWT, where MIT is the actual information or ith information that has been transmitted. Now, if we want to convert this waveform channel into vector channel, we have to employ the concept of signal space that you have already that has already been discussed in our previous day's lecture. So here is a small recap. So if we consider the entire message information to be confined in an n-dimensional space, we need to have an orthogonal basis function for each of these dimensions. Here we have represented each of these basis functions as phi kt. So based on this n-dimensional signal space representation, the entire message symbol can be characterized to be sum of n different components, where each of these components will represent the projection of the overall message symbol into n dimensions. Now, these orthogonal basis functions, they will essentially characterize the actual message symbol vector that has been transmitted. For example, if we are talking about a QPSK symbol that is transmitted over a digital communication channel, then we can easily say that in a QPSK symbol, the message symbol has only 2 dimensions. If we are talking about a MNIPSK symbol, MNIPSK, then it will have m dimensions, which will essentially lead to 2 to the power n symbols. Or we can say that there are m symbols, and which means that the number of dimensions will be log of m base 2. Now that we have talked up, now that we understand that the message symbol is a combination of different projection of the different projection in the different directions of the orthogonal basis functions, the overall message symbol can be simply written as summation of summation of n components, where each component will consist of the orthogonal basis function and its corresponding projection. So the projection can be simply given as the correlation coefficient between the message signal and the basis function. In a similar fashion, the noise that is received at the receiver can also be divided into in-dimensional space, or it can be at least divided into two components. One component will encompass the in-dimensional space that corresponds to the message signal, and the other component which will be in essentially in the null space, or the space that excludes those in dimensions. So the entire message NWT, it consists of two components. The term N0T, which is orthogonal to the in dimensions of the signal space, which means that this component of the noise has effectively no impact on the received signal, and we can essentially ignore it. And the other part, which is in the direction of in dimensions, which we have denoted as NNT here, it similarly consists of in projections of the noise signal in the direction of each of the basis functions. So if we see the entire received signal, what we observe that the received signal, it consists of two components. One component which is in the orthogonal direction to the actual message symbol that has been transmitted, and one component in that encompasses the n-dimensional signal space. The component that encompasses the n-dimensional signal space, it consists of the projections of the message symbol, projection of the noise, which are present in each of these n dimensions, and there is the message in, and there is the noise, there is the part of noise which is orthogonal to that not orthogonal to the signal. So if we want to analyze the entire information that has been reflected or that has been collected at the receiving end, we don't need to bother about the entirety of the message signal that has been received. We only need to bother about the message symbol that has been received in the directions of those orthogonal basis functions, or the message signal that has been received in the n dimensions. If we represent this message signal in the vector form, what we'll see is that the entire message symbol can be represented as a vector R, which consists of the projections of the received message in the n dimensions. So if we represent this entire thing graphically, what we'll see that each of the axes in the graph will represent the direction of each of these orthonormal basis functions, and the individual projections will represent the coordinates of the message symbol that is being transmitted or received. As you can see here, the dotted blue line, which corresponds to the message point, represents the actual direction of the message vector, or we can say that the location of this message point, it essentially represents the location of the coordinate of the message point in the n-dimensional space. Similarly, we can understand the location of the received signal based on the fact that each of the received signal point will be influenced by the AWGN noise which has been added to the original signal, which means that the received signal vector, the red line here, sorry, which means the received signal vector, the red line here, it is essentially the vector sum of the message signal vector and the noise vector. So if we look at the property of this vector representation of the AWGN channel in the received signal, n-dimensional received signal space, what you see that the received signal is sum of two vectors, the message vector mi and the noise vector n, and each of these received signal, each of these have in different distinctive components. Now it is time for us to understand how this property of the AWGN noise. Now, what we know that in the AWGN channel, in general what we assume is that the noise is zero mean and Gaussian distributed, which means NWT is Gaussian distributed and has zero mean. So what does this signify for individual components of the noise vectors in the directions of these orthogonal basis functions? It turns out, if we try to derive or compute the mean of individual components, let us say if we are talking about the component in the kth dimension or in the kth direction in the coordinate in dimensional coordinate system nk, then we can see that the expectation of nk or the statistical mean value, it essentially leads to this integral, which is essentially the projection, which is essentially the expectation of the correlation coefficient in the kth dimension. And since phi kt, which is the orthonormal basis function, is a fixed quantity, everything boils down to the mean value of the noise, which means that the nk will have a zero mean. And since NWT itself is Gaussian in nature and phi kt itself is a constant function, nkt of course will have a Gaussian distribution, will be a Gaussian distributed random variable. In a similar fashion, if we try to understand the correlation coefficient or the correlation between the different components of the noise vector, what we'll see that the expectation of this, it will lead to ultimately the fact that the correlation is zero between different noise in different dimensions, which essentially means that the projection of AWGN noise in each of these dimensions in the received signal spaces are uncorrelated. And of course, since since we are considering orthogonal dimensions, and since the noise itself is Gaussian, it will lead to the conclusion that the noise itself is it consists of independent and identically distributed components. So if we say that the noise in the kth dimension is a complex baseband noise which has a zero mean and variance sigma square, then the overall noise will still be a complex normal vector which has a zero vector for its mean value, and it will have a identity, and its covariance matrix will be a identity matrix whose diagonal elements will be proportional to the individual variances of the components. So if we look at the joint probability distribution of the noise in all n dimensions, or if we want to consider the representation of the probability distribution of the entire noise vector, we'll see that it will be essentially the product of the distribution of the noise in all n dimensions, which is given by this equation, which is 1 by pi to the power n into sigma to the power n into e to the power of norm n square by sigma square. So using this distribution of noise, we can now characterize whatever signal that we have received at the receiving end. So if we assume that we have transmitted, the source has transmitted the ith message vector, which we are denoting as mi, then the conditional distribution of the received signal based on the ith message will be simply Gaussian distributed, but instead of having zero mean, we'll have a message vector mi as the mean of the received signal. So to summarize, what we see here is that the entire messaging system, what we see here is that if we are talking about a waveform channel or a vector channel, if we are talking about a vector channel, the received signal will be based on the n-dimensional signal space. The noise vector itself consists of independent and identically distributed components, and will have a covariance matrix in the form of a identity matrix, And if we want to find the joint distribution of the, and if we want to find the conditional distribution of the received message, it will simply be Gaussian, like as it is for the overall noise vector. The only difference will be will have the distribution translated to the location of the message point. Now, so this is what we get for the vector AWG channel. Then what about the waveform AWG channel? The idea for waveform AWG channel is also very similar, or we'll say that it is essentially the same, except for the fact that we are directly dealing with the waveforms instead of the vectors. So if we have let's say the waveform NWT, sorry, if we have a pardon my bad handwriting, if we have a distribution of the NWT, which essentially gives us a zero bin and variance, let's say N naught, then the received signal R at any point of time will also have a Gaussian distribution with variance N naught, but the mean value, it will be determined by the message signal that has been transmitted. So in this case, if we are transmitting message signal MIT, it will correspond to the message of the received signal. Now that we have a basic understanding of how this works, now that we have a basic understanding of how the waveform AWGN channel or a vector AWGN channel works, and we have my basic understanding of the principle of optimal receiver design, which is essentially the map decision criterion or a maximum likelihood decision criterion. Let us look at the structures of the optimal receivers that we can design for AWG channel. So let us start with the decision rule for the vector AWG channel, which we can subsequently extrapolate to the waveform AWG channel. So as we can see, as we can look at the map decision detection rule, what we see is that the optimum decision essentially leads to the argument which maximizes the joint probability that ith message has been probability that the ith message is transmitted from the source into the distribution of the received signal condition on the ith message. Now, as we have seen that the conditional distribution is essentially a Gaussian distribution, which gives us the fact that we have that the exponential part consists of the received signal and the information message. So if we want to make a decision in favor of the ith message, we need to compare it to the all other messages that are present. So if we look at the actual message that is being transmitted, let us see. What we'll see is that we need to compare it with sorry. We need to compare it with the distribution that ith message is that the distribution for the ith message is essentially greater than the distribution of the any other message that we can encounter from the source, where essentially, so basically here the condition is like this. So if we essentially break it down to the using the conditional distribution that we have just studied, what we'll see is that we have PMI multiplied with sigma n to the power into sigma to pi to the power n into sigma to the power 2n into e to the power minus of norm r minus mi the whole square divided by sigma square. This should be greater than PMJ, which is the probability for the jth source message, multiplied with e to the power minus of r minus mj whole square. As you can see that sigma to the power n and sigma to the power 2n and pi to the power 2n, these components are common, so we can simply remove them. And if we take the logarithm on both sides, the message you will get is that simply will get sorry, what you see is a simplified representation which is being presented using this equation, which essentially shows us that ln of PMI minus 1 by sigma square into norm of R minus MI whole square should be greater than for ln of PNJ minus 1 by sigma square into mod of R minus MJ whole square for all possible values of J which are not equal to I. So if we further divide, if we further simplify, or if we further derive these parts are this part the norm square of R minus mi, what we see is that norm square of R minus mi is essentially the difference of two vectors. And if we look at the graphical representation in the n-dimensional signal space, what we observe is that it is essentially the Euclidean distance between the received signal point and the message signal point. And this distance is essentially caused by the noise that is present in the n-dimensional signal space. So if we further break down this Euclidean distance, what we observe is that we get actually four components. Let us see. The first component is of course PMI, which remains intact. The second component, which comes out from breaking down this Euclidean distance, is the norm square of the received signal. The second component is the norm square of the message signal, and the third component is 2 by sigma square into real part of R Hermitian mi. Now, this real part of R Hermitian mi, it essentially represents the correlation between the received signal and the transmitted message mi. The norm R square, it essentially represents the energy of the received signal. In a similar fashion, norm m square represents the energy of the received message signal. And since this energy of the received signal is independent of the message symbol, so we can simply ignore it, or we can simply remove it from our decision making rule. So ultimately, what we are left with is the log of the source message probability minus the message symbol energy plus the correlation of the real part of the correlation of the received message and the message symbol. And based on whichever message symbol yields the maximum value for this entire term, will make a big decision in favor of that message. Now, so far we have been talking about the message symbol. So since we are talking about the map decision rule, it can also be simplified to the maximum likelihood decision criterion by simply considering the case where all the message symbols are equiprobable. So the map decision in the map decision rule, we can simply ignore the probability of all the messages, and the entire ML detection criterion, it becomes dependent on the Euclidean distance of the received signal point and the message point, or whichever message point has the minimum distance from the received signal point becomes the result of the maximum likelihood detection. So the maximum likelihood detection, it gives us the message point whichever has the minimum distance of the message point from the received signal vector. So here I have summarized the map rule for the vector and AWGN channel, and as you can see, for the vector AWGN channel, the map rule, it essentially consists of three terms: the correlation term, the message signal term, message signal energy, and the probability of the message signal. We can simply replace this entire probability and the message signal power as omega, as a new term omega I, and we can say that for each message, the map rule depends on the correlation of the message and the received signal at this term omega I. Similarly, in case of waveform AWGN channel, we can represent this map decision rule in terms of the correlation in the continuous time domain, which is essentially the correlation between RT and MIT, and ideal part of that, and its summation with omega I. So as you can see that how the optimal detector should be designed for map rule, since we have, or how the optimal detector should be designed, then how do the main fact that becomes that becomes clear, that we need to understand, or we need to derive the correlation between the received signal and the message signal. This correlation between the received signal or message signal, it can be designed in two different ways. One by using a correlation filter receiver, and the other one is the filter based implementation, which is known as the match filter receiver. And depending on what type of AWGN channel that we are dealing with, we have two different distinctive structure for the correlation receivers. One is based on the signal space, which is essentially for the vector AWGN channel, and one is for the correlation definition, which is essentially for the waveform channel. Here I have shown the correlation receiver structures for vector AWGN channel and the waveform AWGN channel. This figure particularly, it represents the correlation receiver structure for the vector AWGN channel. As you can see, we have implemented here a set of filter banks, or the correlator, or we have represented, or we have implemented n correlators. We have implemented n correlators, or a bank of n correlators, which will extract the n different projections in the directions of each of the orthogonal basis functions from the received signal. And using this received vector, we then compare it with the message, individual message symbols. There are n different messages, and for each message we generate the individual correlations, add it with the additional component omega, and whichever has the largest sum will give us the detector output. Now, as you can see that it is a n correlation receiver structure, and more often than not, this structure is used simply because it does not depend on any kind of source. So even if we have a signal which has a much smaller dimension compared to the actual dimension of the received signal, if we have a n correlated structure, it will still work. On the other hand, if we go with the waveform AWGN channel, the entire structure of the correlation receiver will depend on the number of messages that are being transmitted from the source source, which means that in this particular case, we'll not design the correlation structure based on the n-dimensional signal space. Instead, we'll simply correlate individual messages with the received signal, which means if we have m different messages, we'll have m correlators. For most practical design purposes, m is normally greater than n. So it makes sense that the most cost-effective way of designing a correlation receiver is to consider the n-dimensional signal space and in the vector AWGN channel, and design the correlation receiver using the n correlators. Otherwise, the basic the design principle, whether we are considering a vector AWGN channel or a waveform AWGN channel for the correlation receiver, remains the same. Now, let us talk about the match filter receiver design. For the waveform AWGN channel, as we have seen that we have two terms. The first term omega I, which consists of the source probability and the source message energy, and the second term, it explicitly deals with the correlation of the received signal. Now, this correlation of received signal, one thing that we have seen that it can be designed using a correlator. Another way to implement this is to use a filter. So the filter design, as we can see that since we have no way of controlling the received signal, the filter transfer function or the filter impulse response must correspond to the message symbol that has been transmitted, which means that the filter should be matched to the message signal. So if we formally represent the design criterion for a match filter receiver, we can represent the input signal RT as the summation of the overall noise NWT and a generic signal ST, which is essentially going to represent any message signal M1T up to MMT. And if we have the HT as the filter impulse response, the filter output will be essentially convolution between the received signal and the impulse response of the filter. The criterion that we implement for optimizing the filter is to minimize the error is to maximize the received signal to noise power ratio. So if we look at the frequency domain representation of this message signal that or the filter output, what we see is the filter output, it consists of the product of the receive signal in frequency domain and the filter transfer function, which essentially boils down to two parts: the product of the message and the filter transfer function, and the filtered noise response. At any arbitrary time t0, if we want to identify the received signal in time domain, what we'll see that it will consist of the received signal component and the received noise component, and this received signal component can be directly obtained from the frequency domain represented by using inverse Fourier transform to the received signal component. So the filtered received signal component, which means that YNT, the filtered noise component in the time domain at time t0, will be the inverse Fourier transform at time t0 of the filtered noise, and YST0 is the received signal component in time domain at time t0, which is essentially the inverse Fourier transform of the product SF into HF at time t0. And the sampled SNR at time t0 will be simply the ratio of the power of the received signal and the noise components. So if we want to maximize this SNR or the only thing that is in our hand is to maximize the received signal. So if we want to maximize the received signal, we can directly use the Cauchy-Schwarz theorem or Cauchy-Schwarz inequality formulation, which essentially gives us that the entire received signal power is dependent on the received signal energy distribution, and the transfer function response over the entire frequency domain for the filter. And the equality will hold if the filter response becomes proportional to the transmitted signal information, or HF is proportional to S conjugate F. Of course, since we are sampling, or since we are considering the sample of received signal at that time t0, there will be a additional phase in this signal, which is given by e to the power minus j2 by ft naught. This essentially means that the received signal or the influence that the received signal, that in order to detect the received signal with maximum possible signal to noise ratio, we are matching the filter to a version of the transmitted information signal, and this version of the transmitted information signal is shifted and time reversed and conjugate version of the signal. And if we look at the entire message signal, what we see that the proportionality coefficient should be not is normally taken to be 1. So if we look at the variance of the noise of the filtered noise now, what we see that the maximum SNR, it essentially gives us that ratio of the noise and the received signal power. It essentially does not, it essentially bypasses, it essentially is the maximum possible SNR that we can ever achieve in the system. With this particular view, we can now represent the design criterion for a match filter receiver using n correlators or n match filter or n filters. So here you can see that the received signal is passed through in different filters, each of which corresponds to the basis function of the ortho in each dimension, which will lead us to the R1, R2, and Rn, the n different components of the vector, and it will give us the corresponding. It will give us a filter design, receiver design, which is very similar to the correlation receiver design. There is one more thing that I'll talk about after these parts regarding the match filter. What happens when the noise is colored? So when we talk about colored noise, it essentially means that So when we talk about colored noise, it essentially means that the noise power is non-uniformly distributed over all frequencies, non-uniformly distributed at different distributed over the entire frequency range. This essentially means that the noise power spectral density, it does not have a constant value as it has for the AWGN channel. So the the most basic way of dealing with the colored noise is to introduce a whitening filter, which will essentially allow us to convert the transmitted allow us to convert the received noise into white noise, and then implement the match filter receiver or the correlation receiver, whatever type of optimal receiver that we use to decode the information. So if we are talking about colored noise, the entire if we're talking about the colored noise, the entire match filter receiver design or a correlation receiver design, it depends on two components. It consists of two components. The first component is the whitening filter, and the second component that is in cascade with this whitening filter is the actual matched filter that is based on the whitened signal that we receive from the whitening filter. So as you can see here, we have that if we have a noise PSD SNF for the colored noise, and we have a output of the whitening filter as R tilde T, which essentially consists of the whitened noise and whitened signal. So this N tilde T is the whitened noise signal, and it will have a PSD N naught, which is constant at the output, and the overall filter transfer function H1F for the whitening filter will be given by N naught by SNF. So now we can design the match filter receiver based on this S tilde F, which essentially gives us a combination of the transfer function of the widening filter and the receive signal. So the overall match filter design, if we consider for the colored noise, essentially becomes the ratio of the received signal of the transmitted signal distribution in the frequency domain, transmitted signal spectrum, and the noise power spectrum, which of course again is multiplied by a frequency shift due to the addition of the time shift T naught. Now that we have gone through the entire optimum receiver structure and the different forms of AWGN channel, let us talk about the error performance. So the most common way of understanding the error performance, or the most common way of analyzing the error performance, is to define the average probability of error, which essentially encompasses two components. The first component is the distribution of the message signal at the receiver, which is PMI, and the probability of error for individual messages. So we can say that in a digital communication system, we can say that an error has been incurred if we incorrectly identify any message I that has been transmitted as the jth message, which is not equal to I, which means that if let us say that if we have transmitted message M0, which corresponds to the hypothesis H0, and if we make it, we can make a error if we make a decision in favor of a hypothesis Hj, when j not is equal to 0, which means that the error it will encompass the entire observation space except for the decision region for the message M0 or the hypothesis H0. Now this is the generic idea of how the average probability of error works. Now let us consider a few specific cases. The first special case that we are going to consider is the optimum receiver for binary signaling, which essentially means that we have exactly two distinct read messages that have been transmitted, and we are going to check the optimum decision rule for this type of messages. Now the optimum decision rule or the map rule for this message or for this binary signaling, it consists of the fact that the Euclidean distance of the message 1 from the received signal and message 2 from the received signal needs to be compared, and the one whichever is closer to the received signal will make a decision in favor of that one. And as you can see in this particular diagram, the received message is at a distance mu from the message symbol M2, and the overall distance between the two messages is D. So the distance between message M1 and R, or the received signal point, is D minus mu. Now if we use this particular concept, or if we use this particular statistics here in the optimal decision rule, what we'll see that everything corresponds to any decision that we can make, or we can we can resolve this entire decision rule in terms of mu and d, and it shows us that as long as mu value is greater than this particular value, we can make a decision in favor. Sorry, I think we have made a small mistake here. It should be M1 and it should be M2. So as long as it is this mu value is greater than this particular decision, so we'll make a decision, and this should be plus, I think. So we'll make a decision in favor of M1, and if it is less than this particular value, we'll make a decision in favor of M2. And from this particular case, we can generate the probability of error in a AWGN channel by using the Q function and the individual symbol transmission probabilities. So what we see is that this is the case for the map decision rule with a binary signaling where the messages are not equiparable. So what happens when the messages are equiparable? Again, we don't need to consider the individual components again. So PM1 and PM2, they will be equal to half. So PM1 is equal to PM2 will be equal to half, and the value of mu, it will converge to 0. So essentially the decision threshold will converge to 0, or the decision threshold will be simply like this. And since the decision threshold is based on the origin or the boundary of the decision boundary, the values of these individual Q functions will become equal. So the overall binary signaling probability, error probability, will be given by this single Q function, which isn't single Q function, which essentially gives us the ratio of the half of the distance between the signal points and the square root of the noise power spectral density. Now, this leads to an important observation, is that for any kind of binary signaling, as long as the points are equiprobable, we don't need to go through all the entire process of determining the decision region and then finding the individual symbol error probabilities. We can, for AWGN channel, we can simply state that the error probability will be given by this Q function, which whose argument is essentially dependent on the half distance between the signal points and the ratio of the square root of the noise power. Now this leads to the fact that, okay, this was the case for only the binary signaling case. What happens when we have a multidimensional signal space, or when the signal space does not have any regular decision boundary structure? In such a case, determining the exact error probability for the multidimensional signals is very difficult. For example, if we consider, let's say, the signal constellation diagram that has been shown here, it consists of it is a pi by 4 QPSK symbol, and it consists of two distinct dimensions and 4 symbol messages. So if we want to determine the error probability for message M1, we need to compare it with all 3 distinct messages, and only then we can decide on what is the error probability for the message 1. And this is not exactly a simple straightforward process. So there has a method has been introduced to deal with this type of scenario where the decision boundaries are not exactly straightforward, and the decision regions cannot be directly determined. So instead of going through the relation between instead of going through the relation between the message point M1 and M2, then M1 and M3, then M1 and M4, the idea that was introduced is to consider the pairwise error probability, or the pairwise error. So here what we'll do is that we'll consider 3 distinctive set of cases where we'll consider the error for individual messages. The first case will consider the combination of the message M1 and M3. The second case will be message M1 and M2. And the third case will be message M1 and M4. And all these 3 distinct cases will cover all the different error possibilities for message M1. And as we can see, the moment we reduce this entire message set to 2 distinct messages, it becomes a binary decision process for individual sets. So here we are making a binary decision on whether we have an error or not. And if we combine all these 3 scenarios, if we combine all these 3 scenarios, what we see that we are covering the decision region more than what should be covered for the message M1. So what we can say essentially that if we combine the error obtained in these three cases, they should give us an upper bound on the what actual error should be for the message M1. Here I have here I have shown how the union bound for this union bound works. So if we look at the message here, so this part of the message, it consists of the error probability for the ith message, which we need to transform to the error probability for the ith message using the individual pairwise error probability conditions. And as we have seen here, instead of using the actual decision region Z1, Z2, Z3, we'll be using these alternate decision regions A1 2, A21, A3, A1, A31, A13, A41, and A41, A14. And as you can see from our diagram that any actual decision region is actually a subset of these alternate decision regions, which means that the overall error probability considered for each of these binary decisions will exceed the actual error probability that is present in sorry, this is not just for the single binary decision, so this should be for all the binary decisions for the ith message. So essentially what we have is the overall error probability. It can be upper bounded by this alternate version of the error probability calculation, where we'll be making a binary decision based on the relation of the intended message that we are considering and the all other messages. And if we consider a maximum likelihood detector, which is essentially the case for the equiprobable signals, the individual basis probabilities will reduce to 1 by m, and we can further simplify it, the decision using the Q function, which is essentially the individual distance between the ith message and the jth message in the signal space constellation. This Q function can further be upper bounded by using the exponential function, which will give us a more which will give us a a further upper bound on the overall probability process. Now this upper bound is very useful in understanding what the error probability should be for any kind of multidimensional signal space that we can design for digital transmission system. With this, I will conclude our discussion on the optimal deceiver. So if there so since we have some time remaining, we can take in some questions. If you have any queries, please go ahead.
Thank you, Sudarshan sir. So participants are requested to please put your queries if you have any queries in the Q&A section so that sir can address your queries. Santosh Kumar sir, the presentation slides is already like told. It will be given to you. You can find the presentation slides in the drive link. Day-wise materials will be uploaded in a drive, so you may go through the drive link after the session. Thank you.
Hey, Firoza, sorry. Firoza, can you hear me?
Yes, sir. Yes, sir.
Somehow my share window is disabled. I cannot share content.
Yes, sir. Now the presentation is with Sudarshan sir.
Okay,
So
okay.
it's sir, just few minutes. So we'll be sharing the rights with you.
Okay, okay, fine, fine, fine.
Yeah. Thank you, sir.
Okay. If so, I don't know. So if anyone has any questions, you can ask me. And as Ms. Proja said, that the present slides will be shared through a drive link. And when the slides are shared, I will also send a Microsoft form link for or for a few MCQ type questions with answers.
Dr. Mukherjee,
Yes.
This is Shabyasachi from Borakville College, Karimganj.
Yes, Sabhayaji.
Yeah, sir. During your presentation, I had a question. You were showing different modes of the AWGN channel, in which you were
Right.
showing a vector AWGN channel, and also there is another nomenclature that you presented. So,
Yes.
why are these separate modes of the AWGN channel necessary in the analysis? Like, or the regular analysis is like, why these additional vectorization of the AWGN channel? Why is it actually necessary? I had a small doubt in that actually. Yeah.
You see, the vectorization of the AWGN channel is, you see, that when we talked about a waveform AWGN channel and a vector AWGN channel, right?
Yes, sir. That waveform AWGN channel. Basically.
The waveform AWGN channel, it actually the treatment of the AWGN channel using the original waveform, original analog waveform that we are receiving. Okay. So it is essentially by, without any form of digitization or anything. So we are using the direct signal that we are receiving and treating it as it is to detect the symbol. Now the vector AWGN channel compared to the waveform AWGN channel, it has a little bit difference. The difference is that if we want to go about with a direct AWGN channel, it not only considers, it not only considers information from the all different dimensions that we have already transmitted. For example, the received signal space that we have considered, it only has n dimensions, right? So, but the noise in the waveform channel, it does not consider it is not only limited to the n dimensions. It also has other dimensions which are outside the message space. Now, when you are actually dealing with a practical system, you don't have a single message that is being transmitted.
Okay.
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 So
Okay. Yes, sir.
whenever you receive a signal, you'll see that there is a host of messages coming, and you need to identify your signal which are present in a particular set of dimensions. So any information that is present, any noise that is present outside those dimensions are irrelevant to you. And if we allow if we actually try to if we actually try to handle all of them simultaneously, it is actually better to handle all, instead of handling all of them simultaneously. It is actually better to limit your system to only those n dimensions, because anyway you are going to deal with a band limited channel, right?
Yes, sir. Yes. Sir,
So
it means that since in the n dimension, the signal is composed of only n dimensions as per the n
right,
number of orthonormal basis function, the noise
right,
also we are considering only in those n dimensions and not in all the possible dimensions that may exist. That is what
yes,
the thing? Yeah.
yes, that is the and the main point is that
Yes.
when you are considering a digital transmission system, your actual information is digitized, right? So
Yes,
you
sir.
do,
Yes.
so it is better to so it is better to deal with the digitized information and digitized receipt signal
Yes.
than
Yes.
to have deal with the waveform,
Waveform.
because
Yes, sir.
whenever there is a change in the dimension space, the entire receiver structure will have to change according to the waveform. But if we have a vector representation which is obtained after extracting the everything associated with the dimension and orthogonal basis functions, you don't need to change the code structure. You can implement that code structure anywhere,
Yes, sir.
right?
Yes. Yes, sir.
So that is why we have a vector representation which actually represents the digitized hardware where the actual data detection is being taking place.
Okay. Yes. Okay.
So
Okay, sir. Okay. Thank you so much, sir. Thank you.
yeah.
Uh, uh, Thank you, sir. So we have one more query from the participants.
Yes.
So, like she wants to know, so among all the methods discussed during the session, which method is better for error detection and correction?
Uh, for error detection and correction, you see, whenever we are talking about let's say, whenever we're talking about error detection and correction, it of course depends on how we design the receiver, right? So when we are talking about the optimal receiver, we normally, as we have already seen, that we normally consider the map detector or the email detector. Now, when we are talking about a binary decision making process or a binary decision or a binary transmission system, of course, the method of detecting the error is very straightforward. It is from the map decision we can directly obtain a fixed decision rule according to which we can make a decision. So there is no confusion in that. But when you have a multidimensional signal space, it becomes very difficult to actually measure the error probability. That's why we introduce the union bound. But that does not mean that we cannot ever measure the union. We cannot ever measure the actual error probability. There is, for example, the instance that I gave you, just showed you, is of QPSK. With QPSK, of course, we can go about using a union bound and we can generate a bound on the receive signal error probability. But we can also determine the correct probability of obtaining a correct signal and subtract it from the origin, subtract it from 1 to obtain the actual error probability. To obtain the actual error probability. Does that make your answer? Does that make your query clear?
Thank you, sir.
Yep.
And sir, another question from Miss Archana Bhange. Sir, can we use both matched filter and coherent receiver for coherent and non-coherent receiver?
When we're talking about coherent and non-coherent receivers, you have to understand what it actually means. When you're talking about coherent deceiver, it means that the entire thing, it has been actually synchronized with the received signal and the transmitted signal, which means that you have exact which essentially means that you have exact details of whatever information that has been transmitted. Sorry, it is a let me put it in a better way, that if we talk about a correlation receiver or a match filter receiver, it essentially means that you have exact information on whatever message that has been transmitted, and you have designed your filter in the similar fashion, which means that you have exact control on whatever when the signal is being received and whatever it has been received, and there is no missynchronization between the transmitter and receiver. So for coherent receiver, you can always use the match filter and the correlation receiver. Now, if we talk about non-coherent detection and non-coherent receivers, they are different things. If we are talking about non-coherent receivers, they are not synchronized. They are not directly synchronized with the actual signal. But if you still use the correlation, you can still use the correlation receiver and the match filter receiver. But obviously, due to loss of synchronization, some error will always creep in your performance. So I think that should clear your question.
Okay, thank you, sir. So I think so that was the last question. So, sir, can we end this Q&A session, sir?
Yeah, sure.
Yeah. So with this, we would like to thank Sudarshan sir for such a wonderful talk. So we will be starting with the next session. The next session is being delivered by Dr. Shalil Kashyap, sir. Dr. Shalil Kashyap is a faculty in the Department of Electronics and Electrical Engineering at IIT Guwahati since 2017. Before joining IIT Guwahati, he was a senior DSP engineer at Marvell, where he has designed physical layer algorithm for the next generation wireless LAN protocol. Prior to that, he was a postdoctoral researcher at Linköping University, Sweden, and he received his PhD degree from IISc Bangalore, MTech from IIT Guwahati, and BTech from NERIST. His research interest areas are wireless communication and signal processing. With this, we would like to invite Shalil sir to please start the session.
Okay, I'm audible now.
Yes, sir, you are audible, sir.
Sir, one request is that if you can share your whole screen. So because if you share only a particular application, and if you're opening any other tabs like either the chat box or the Q&A windows, so that portion of the screen is getting gray. So it's not visible to us. So is it possible, sir, if you can share your whole screen, then that problem will not arise?
Okay, so do you, so is my screen not visible?
So your screen is visible, sir. Like since you have selected a particular application, so after sharing your screen, whenever you're opening any other windows, like either the Q&A windows or the participants window, the like that portion of the screen is getting gray.
Okay, okay. So is it fine right now?
Uh, yes, sir. Okay.
Okay, yeah, yeah. I'll take care of that.
Okay.
So,
Okay, sir.
fine. So can I start now?
Yes, sir. Sure, sir. Thank you. Thank you, sir.
Thank you. Yeah, thank you for the kind introduction. So, all right. So in this talk, what we'll do is we'll talk about representation and characterization of a fading channel, and then we'll take up few examples to discuss digital communication over fading channels. All right. And broadly, this is going to be the plan of the talk. In the first, so the talk is divided into two parts. In the first part, we'll see how basically we characterize a wireless channel. All right. How do we model a wireless channel? And in the second part of the talk, we'll take up few examples to elucidate a digital communication over fading channel. All right. Okay. Now, very quickly, to understand the various physical phenomena that a signal undergoes when it travels over the air between the transmitter and the receiver, yeah, we should understand that whenever signal goes over the air, it's the strength of the signal, it varies with time and frequency. All right. There are broadly two kinds of propagation effects. One is the large scale propagation effect, in which the variation of the signal strength occurs over larger distances. Yeah. And then there is the small scale fading effect, where the variations in the signal strength, they occur over very short distances of the order of wavelengths. All right. Now, what all phenomena comprise or constitute large scale fading? So fading essentially is the variation in the signal strength as it travels from the transmitter towards the receiver. So the signal can undergo a decay in its strength as a function of distance. Yeah, and this is something that we term as path loss. The signal may suffer from attenuation due to reflection, absorption, diffraction, scattering due to obstacles present in the environment. All right, and this is what constitutes shadowing. All right, and these large-scale propagation effects consisting of path loss or shadowing, they basically help us decide the power levels that are required for transmission on the uplink or on the downlink. They also help decide coverage of base stations, how must a cell be planned, cell site planning and all that. Yeah, basically where must a base station be placed so that the performance of the network is optimum. Then there is this other effect which is called as small scale fading. So essentially what happens is that when a signal X is transmitted from the, is sent out from the transmitter, multiple copies of the same symbol is received at the receiver. Yeah, and that is because there can be multiple paths through which the signal can travel. So there can be a line of sight path. The signal from the transmitter can go hit a reflector and reach the receiver, can go hit another reflector and reach the receiver. So, so we should basically understand that there are multiple paths between the transmitter and the receiver through which the signal can travel. All right, and each of these paths, the amount of distance traveled by the signal can be different. Yeah, accordingly, different paths may introduce different kinds of amplitude changes and phase changes. Now, the multiple copies of the same signal that is received at the destination, in case they add up in phase with each other, then it results into constructive interference among those multiple copies of the same symbol and may boost the signal strength. If these multiple copies add out of phase with each other, then what we notice is destructive interference and a reduction in the signal strength. All right. Now we should understand that the wireless environment is highly dynamic in the sense that there could be relative motion between the transmitter and or the receiver, or the reflectors can themselves be moving around. So the pattern of constructive and destructive interference, it repeats. Yeah, I mean, at certain time instants, the signals may add up in phase with each other. At certain other time instants, the signals may go out of sync, and this is what brings about variations in the channel strength. All right. Now this is something that varies at a much faster time pace. Yeah, and this is what is important to design. Yeah, this is what we should take care of while designing reliable and efficient communication schemes. Yeah, any of the modulation, coding, or detection schemes that we talk about, they care about these small scale fading effects. Yeah. Large scale fading effects mostly have to do with cell site planning and deciding on the power levels that is required for transmission. All right. So So understand that with fading, what we mean is the variation in the signal strength as it travels from the transmitter to the receiver. Okay, and these variations can be due to multiple factors. One is path loss, the other is shadowing, or there could be constructive and destructive interference among the multiple copies that reach the receiver. Multiple copies of the transmitted signal that reach the receiver. All right. Yeah, so I hope my full screen is visible. There is nothing getting cropped. Can
No,
somebody?
so it's visible.
Okay, good. Yeah. So let us try to understand what is the need to model or characterize a wireless channel. Yeah, it is important to characterize or model a wireless channel primarily because of these factors. We need to understand what modulation and detection techniques must be used. We need to understand where must the base stations be placed so that a uniform quality of service can be given to all the users that are present in the network. What is the power level that must be used either on the uplink or on the downlink? Yeah. If we know how to model a wireless channel, we can try understanding the role played by various physical phenomena that we talked about in the previous slide. Yeah, it is. It then makes it easier to do some performance analysis and benchmarking. All right. Okay, so what we'll do is, what we'll do in the next few slides is we'll take up a few toy examples to illustrate the kind of wireless channel you can expect to have depending on the environment you are in. All right, and we will, instead of doing wave propagation analysis through Maxwell's equations, we'll stick to doing it with the approach of ray tracing, where we'll basically write down the received signal as a sum of responses from different paths. All right. Now these toy examples, although they are simple in nature, they do give us an intuitive understanding of the channel behavior that one can expect in practical scenarios. Okay. So yeah, so throughout this talk, we'll take up several examples to understand how wireless channel behaves depending on the scenario we are in. So the first example is that of, is the scenario where, let us say that the transmit antenna and the receive antenna, they are fixed, all right, they are not mobile, and the signal travels over free space between the transmitter and the receiver. Okay. Now a quick look at this cartoon here. So what we show here is that the transmitter is located at the origin. Yeah, and it is fixed. The receiver is located at a distance r from the transmitter. Yeah, this particular angle is theta and this angle is psi. Yeah? So the coordinates of the receiver are given by r, theta, and psi. And note that both are static. All right. Now let us say that a signal cosine 2 pi ft is sent out from the transmit antenna. Okay, so what is it that we are doing here? We are sending out a sinusoid from this transmitter. Yeah, let us see what is the response at a receive antenna which is fixed and is located at r, theta, psi. Yeah, so the response at the receive antenna would be the signal that is sent out, and the signal will be delayed. All right, it will be delayed by an amount equal to what will be the delay? The delay will be equal to the distance that is that this signal travels divided by the speed with which the signal goes over free space, okay, which is c, the velocity of light, or an electromagnetic wave. So so cosine 2 pi ft is sent out from the transmitter. What is received at the destination is a delayed copy of this same signal. Yeah, and the delay is proportional to the distance that the wave that the signal travels, or the waveform travels, divided by the velocity, all right, with which it travels. Then as the signal travels over free space, it undergoes an attenuation. Yeah, and so this divide by r captures that particular effect. And then there is a pre-scale, then there is a scaling by alpha, theta, comma, psi, comma, f. Yeah. So what this does is it captures the product of the antenna radiation patterns along theta, comma, psi, along this direction at frequency f. Okay. So we understand that when a signal cosine 2 pi ft is sent out from the transmitter, it undergoes an attenuation, yeah, depending on the distance it travels. There is a delay associated with the signal, or in turn, the phase of the signal varies by an amount f times r by c. Yeah, so the phase varies as r changes. And we also understand that the received power, it decreases as r square, r minus 2. Okay. Yeah, so now if for a given u, yeah, for a given location of the receive antenna, if we define a function h of f as follows: alpha theta comma psi comma f exponential minus j 2 pi f r by c divided by r. All right. So for a given u, if we define h of f as follows, then the response at u in terms of this function can be written down as the real part of hf exponential j 2 pi ft. Yeah, if we plug it here, we understand that this is nothing but this is nothing but the real part of h times f defined this way times exponential j 2 pi ft. Now, so the point is as follows. So if you look at this this thing here, yeah, so the broader picture is as follows. You can regard the wireless channel in this particular scenario where the transmitter and the receiver, they are fixed and signal propagates over free space. You can regard this channel as a linear time invariant system. Why is that so? You feed in a signal, or you feed in a sinusoid at frequency f. What you obtain at the output is also the same sinusoid at frequency f, albeit with a scaling. Yeah, and the scaling h of f equals this. Yeah, it depends on the distance that the signal travels as it moves from the transmitter to the receiver. All right, so this is the scaling which is associated with the sinusoid as it reaches the receiver. All right, and we can clearly see that this does not vary with time. Okay, so the frequency response is frequency response of this system does not vary with time. Yeah, so we are looking at basically a linear time invariant system. Yeah, it is linear because to get the scaled input at the output. Yeah. So you feed in a sinusoid, what you get at the output of. So visualize this wireless channel as an LTI system where the transmitted signal is a sinusoid at frequency f, and the received signal is the same sinusoid at frequency f, but with a scaling, and that scaling depends on the frequency response of the system. Yeah, and the frequency response, we can clearly see that this does not vary with time. So the key takeaway is, that when signal propagates from a fixed transmitter towards a fixed receiver located at a distance r, the wireless channel behaves as a linear time invariant system. It does not inflict any change in frequency. Yes, depending on the distance traveled, there will be a change in phase of the transmitted signal. All right, and the magnitude will also change. Yeah, so hf mod equals alpha by r. If you look at the magnitude of this, it is alpha by r. Yeah, and this is the magnitude. We can clearly see that this is independent of frequency as well. Okay, so this was the scenario when we have fixed transmitter and receive antennas. If anybody has any questions, I can take it up. Any questions so far?
Participants, if you're having any questions, please put in a Q&A section.
Okay, so do we plan to take it towards the end?
Yes, sir, we may take now as well as at the end also,
Okay,
sir.
okay. Yeah, so please feel free to ask questions if you have any. Yeah, I'll continue. Yeah, so the second model is as follows. So what we now analyze is, let us say that the transmitter is located at the origin, all right, and the receiver is located at a distance r from the transmitter, r of t. Yeah, so the receiver is located at a distance r of t. We are now considering a scenario where, let us say that the receiver moves with a velocity v in a direction that is away from the transmitter. All right, so the receiver moves with a velocity v in a direction away from the transmitter. So its distance at time t relative to the transmitter is given by r of t. All right, and that r of t is a function of time. Yeah? It is equal to r naught plus vt. Yeah? So essentially at time t equals 0, the receiver is located at r naught. However, as time progresses, the distance of the receiver relative to the transmitter equals r naught plus velocity with which the receiver is moving, multiplied with the time elapsed. All right. So what is the difference relative to the scenario that we considered under toy model 1? Here the receiver is mobile. Okay, we are still in the free space propagation environment. Let us now try to see how the wireless channel behaves in this scenario. Okay, so in a similar fashion, let us assume that a sinusoid at frequency f is sent out from the transmit antenna. What will be received at the receiver, whose coordinates u of t equals rt theta comma psi? It will be what? Cosine 2 pi f t minus the distance traveled by the sinusoidal waveform at time t divided by the speed with which that waveform travels as it moves from the transmitter to the receiver, divided by r of t. All right, so this is roughly the attenuation that the waveform suffers from. This captures the effect of the radiation patterns. And yeah, so you send out cosine 2 pi ft, it undergoes a delay depending on the distance that it travels. If we plug in rt equals r naught plus vt, what do we get? We get 2 pi f times t minus r naught by c minus vt by c. Yeah, and that is what is written here. So plug in for rt equals r naught plus vt. So what do we notice? We notice the following. Unlike the previous scenario where the receive antenna was fixed, yeah. So when the receive antenna when both the transmit and the receive antennas are fixed, you transmit a sinusoid at frequency f, you will receive a sinusoid at the same frequency f. There will be phase and amplitude changes, all right, and the system behaves as a linear time invariant system. However, if the receiver is mobile, yeah, and it moves with a velocity v away from the transmitter, you feed in a sinusoid, what you receive, so you feed in a sinusoid at frequency f, what you receive is a sinusoid at a different frequency. Yeah, so the sinusoid at frequency f is translated to a sinusoid at frequency f times 1 minus v by c. Okay. So the signal basically suffers a Doppler shift of minus fv by c. Yeah, and this minus sign essentially indicates that the receiver is moving away from the transmitter. Okay, so minus sign captures the effect that the motion of receiver is, the receiver is moving away from the transmitter. Yeah, you can compare it to the case of a ambulance. As it moves towards you, you notice a stronger siren. As the ambulance moves away from you, you notice a feeble siren. Yeah, because the frequency goes down. So yeah, so the point is, you send out a sinusoid at frequency f. What you receive is a sinusoid, but at a different frequency. And the amount by which the frequency gets translated, it depends on the velocity with which the receiver is moving. Okay, so there's a Doppler shift that is introduced, and this Doppler shift is proportional to the velocity with which the receiver is moving. Okay, so we are now looking at a scenario where the frequency response of the system is no longer independent of time. Yeah, it essentially varies with time. Yeah, and what is the variation? It is captured here. So for a given ut, if we define h of f comma t, the frequency response of the system in this manner. Yeah, so the response in terms of the frequency response will be hft exponential j2 pi ft. Yeah, so you get a sinusoid at a different frequency. Yeah, and the translation depends on the velocity. And we can clearly see that the frequency response is no longer independent of time. It varies with time. Yeah. So the takeaway message is, when we have a receiver, or it can be the other way around as well. So the point is, if there is relative motion involved between the transmitter and the receiver, then the wireless channel varies with time. Okay, wireless channel varies with time, and the variations and how fast does the channel vary with time? It depends on the velocity with which the receiver is moving. Okay, so we can clearly see that if the velocity with which the receiver is moving is high, the Doppler shift associated is high. Yeah, the frequency will undergo a larger translation and so on. Yeah, so unlike the fixed transmit receive antenna scenario, where the wireless channel behaves as a linear time invariant system, when we are looking at a scenario where there is relative motion between the transmitter and the receiver, the channel is no longer LTI. It is a linear time variant system. All right. Now, to give you a feel for numbers, let us say if we have a receiver that is moving at 10 meters per second, yeah, and let us say you transmit a sinusoid at 2 gigahertz, yeah, or the frequency of operation is 2 gigahertz, then the Doppler shift that you can expect is 66.6 hertz. All right, so that is the amount of translation you can expect when you are in a scenario where there is relative motion involved between the transmitter and the receiver. Okay, anybody has any questions so far? Okay, if not, let us take up another example. So what is it that we talked about so far? So we have looked at the scenario where these two are static. I guess I'm audible, right? There is no issue at the other end.
No, sir, you're audible.
Okay, okay. Yeah, while giving webinars, you get the feeling that you're talking to a blind screen and then you don't realize. Fine. So we have looked at a scenario where both transmitter and receiver, they are fixed. Then we looked at a scenario where the receiver is mobile, transmitter is static. Let us now introduce a reflector in the environment. All right. So let us say that as before, we have a transmit antenna that's fixed. We have a receive antenna which is fixed. And in addition, there is a wall or a reflector that's present in the environment. Yeah. Yeah. And we want to understand what to expect from the wireless channel when we have transmit and receive antennas that are fixed and there is a reflector present in the environment. Okay, in this case the reflector is a wall. Okay, as before, let us say that a sinusoid at frequency f is sent out from the transmit antenna. Then what will be received here at the receive antenna, which is located at a distance r from the transmitter, and the distance between the transmit antenna and the wall is d, let us say. So the response at the receive antenna located at a distance r from the transmitter will be what? So the sinusoid, it will be delayed. So it will essentially be now a superposition of two components. Yeah. So this transmitted signal can reach the receiver via this path, which is called the direct path, or it can reach the receive antenna via after hitting the wall. Yeah. So via the reflected path. Okay. So accordingly, the response at the receive antenna located at r distance from the transmitter will have contribution from the direct path and the contribution from the reflected path. Along the direct path, the signal undergoes a delay of r by c. Yeah, this is the distance traveled by the signal along the direct path. And along the reflected path, it undergoes a delay of d plus d minus r, which is essentially 2d minus r by c. Okay, so these are the two components. Along the direct path, the attenuation is r. That's the distance traveled. And along the reflected path, it travels a distance of d plus d minus r, which is 2d minus r. Alpha, as before, captures the effect of antenna radiation patterns. Yeah. Okay, I hope it is clear. So we can clearly see that what have we done? We have written down the response as a linear combination of responses or signal received from different paths. In this example, we have two paths along which the signal can travel and reach the receiver. let us try to analyze this system in a little more detail. Now, if we do that, what is the phase associated with the reflected path? It is 2 pi f times 2d minus r by c, okay, plus pi. Yeah, that's the phase associated with the reflected path. Why do we have an additional pi? We have an additional pi because the signal after it hits the wall, the direction of the electric field is reversed. Yeah, so to capture that effect, yeah, this minus sign has been put. Yeah, in general, it is just a superposition of the signal via different paths. Yeah, and therefore this this pi captures that effect, the direction of the electric field getting reversed after the signal hits the reflector. And then what is the phase associated with the direct component? It is 2 pi f times r by c. Yeah, so we are interested in finding out the phase difference between the copies of the signal received by the two paths. Yeah, so this is the phase associated with the reflected path. This is the phase associated with the direct path. And if we simplify this, we get something like this. Yeah, so the phase difference of the signal received by the two paths is this 4 pi f times d minus r by c plus pi. Okay. Now, as long as this phase difference is an integer multiple of, or is an even multiple of pi, yeah, 2n times pi, which means as long as the phase difference is an even multiple of pi, what can we expect? We can expect these two copies of the transmitted signal to add up in phase with each other, and the strength of the received signal will be boosted. All right. If, however, the phase difference between the two components is an odd multiple of pi, yeah, then we expect that these two components will essentially kill each other. All right, and we expect destructive interference to happen. The received signal will grow weaker and weaker. Okay, so this is essentially small scale fading. Yeah. So depending on, so what all does this depend on? So we can clearly see that this phase difference depends on the distance that is traveled by the wave, yeah, as it reaches the receiver. It is a function of the frequency at which you are operating. All right. So distance matters. Yeah. Depending on the distance traveled, the amount of phase can be determined. So as a function of R, we clearly understand that there is a pattern of constructive and destructive interference. Yeah. To be precise, delta theta, what do we have? So delta theta is 4 pi f times d minus r by c plus pi. Yeah. Now we know that f by c is nothing but the wavelength of the signal. Yeah. So 4 pi times d minus r by lambda plus pi. Now if you stare at this carefully, what we understand is that if d minus r increases by lambda by 4, yeah, if you plug in d minus r equals lambda by 4, then we notice that delta theta increases by pi. Okay. So if the two waves were adding up constructively, the moment the waves travel, the moment d minus r increases by lambda by 4, they may start adding up destructively. Okay. So the point is, as long as the change in distance is much lower than lambda by 4, there is not much change in delta theta. Yeah, sorry, there is a typo here. They should have been delta theta. Okay, so as long as the change in distance is much lower than lambda by 4, there is not, as long as the change in distance is much lower than lambda by 4, you'll not notice an appreciable change in the received signal. Okay, and therefore this quantity, yeah, approximately is termed as the coherence distance. Yeah, this is the distance over which the change in delta theta is small, or in other words, this is the distance over which, if the wave travels, you will not notice any substantial change in the received signal. All right, that is why we term this as coherence distance. The same quantity here, if we observe it as a function of f, so as a function of f, this is what, 4 pi f d minus r by c plus pi. Now for delta theta to change by pi, the frequency should change by an amount c by 4 times d minus r. Yeah, if you plug in f equals c by 4 times d minus r, you notice that the phase will change by an amount pi radians. Yeah. So as before, so in terms of distance, as long as the distance does not change by substantial, I mean, as long as the change in distance is much smaller than lambda by 4, you don't notice an appreciable change in theta, and that is why this distance is called as the coherence distance. In a similar way, as long as the change in frequency is lower than this amount, you do not notice an appreciable change in the received signal, and therefore this frequency is roughly called as the coherence bandwidth. Yeah, so there's the range of frequencies over which the channel roughly behaves as a constant. All right. Okay. So yeah, so what is the scenario we are looking at? We are looking at a scenario where both the transmitter and the receiver, they are fixed, and then there is an additional reflecting wall, yeah, perfectly reflecting wall present in the environment. And we have already seen that the response at this receive antenna is a superposition of two components, one received by the direct path and the other by the reflected path. And as before, this can be written down as real part of HF exponential j2 pi ft. What do we notice? Yes, we have sent out a sinusoid. What you receive is the sinusoid at the same frequency, just that there are two copies received. Yeah, and the frequency response of the channel is what? Yeah, so h of f equals alpha by r exponential minus j2 pi f r by c. So when the signal travels along the first path or the direct path, it undergoes a phase change captured by this f, I mean 2 pi times f times r by c. When it travels along the reflected path, the amount of phase change is 2 pi times f times 2d minus r by c. All right. This is the attenuation suffered along the reflected path. This is the attenuation suffered along the direct path. Yeah. So that's the frequency response. You can clearly see that this is independent of time t, and therefore we are still so as long as the transmit and the receive antennas, they are static, yeah, there is no motion involved, you can classify the wireless channel as a linear time invariant system. The addition of a reflector just gives you additional copies of the transmitted signal. All right. If you take the inverse Fourier transform of this, you get the impulse response. Yeah, impulse response is what? The response obtained when you apply an impulse signal to the system. So h of tau will be alpha by r delta t minus the distance traveled divided by the velocity. Distance traveled along the direct path divided by the velocity with which it travels. And then there's an additional path along which the signal travels a distance of 2d minus r, and therefore the delay associated with this will be 2d minus r by c. Okay. Yeah, so this is what this is an environment where there are two paths, two physical paths along which the signal can travel as it moves over the air from the transmitter to the receiver. Okay, you get two distinct copies. The two copies reach at different time instances. All right, one copy is delayed by an amount r by c, the other copy is delayed by an amount 2d minus r by c. The direct copy undergoes an attenuation of alpha by r. The reflected copy undergoes an attenuation of alpha by 2d minus r. All right. Yeah, so there's a simplistic scenario where there are exactly two paths through which the signal can travel. And then again, there is a parameter called as the delay spread, which captures the difference in the delay associated with the two paths. And in this case, the difference in delay associated with the two paths is 2d minus r by c minus r by c. Yeah, this should have been a minus r by c. This equals 2 times d minus r by c. And yeah, so yeah, so the delay spread, it captures the difference in the delay associated with the two paths. And if you look at, if you stare at these formulas, you'll understand that this is inversely related to the coherence bandwidth. All right. So the larger the delay spread, so the larger the delay spread, Rajesh, I'll call you back. I'm actually, I'll call you back. Yeah, so so the delay spread is inversely related to the coherence bandwidth. The larger the delay spread, the smaller is the range of frequencies over which the channel essentially behaves as a constant, or the channel gain is constant. Okay. Yeah. So what have we done so far? We have discussed three different models. The first model was when the transmitter and the receiver, they are static. They're both static. We understand that in that case, the channel behaves as a linear time invariant system. We then looked at a scenario where there's relative motion between the transmitter and the receiver. We figured out that the channel behaves as a linear time varying system. The moment we add a reflector to a scenario where both the transmitter and the receiver, they are static, the channel is still, since there's no relative motion involved, the channel is still linear time invariant. However, things like delay spread shows up. Yeah, so you get multiple copies of the same transmitted symbol, unlike the case where there were no reflectors. Okay, the channel is still linear time invariant. Let us look at a slightly more involved model where you have a transmitter. There's a perfectly reflecting wall present in the environment. And then there is a receive antenna that is moving with a velocity v away from the transmitter and towards the wall. Right. So, all right. So I hope the distinction between this and the previous model is clear. And now the receiver is also mobile. There is a reflector as well present. So there are parameters like coherence time, which can be characterized. Coherence time is roughly the time duration over which the channel characteristics are constant. Yeah, they're invariant. Okay, and this is related to the coherence distance divided by the velocity with which the wave travels. We can simplify and write it as c by 4 fv. The channel variations remain constant if the transmission time is much smaller than the coherence time. Now, to get a feel for numbers at a frequency, if the frequency of operation is 900 megahertz, and let us say that the receiver is moving with a velocity of 3 kilometers per hour. Yeah, if you plug in these numbers here, one can find out that the coherence time is of the order of hundreds of milliseconds. Okay. Yeah. So now, so this was again just a jargon. Yeah, it gives you an idea about the duration over which the channel characteristics essentially remain constant. All right. Now, if we look at this scenario, as before, let us say cosine 2 pi ft, a sinusoid at frequency f is transmitted from the transmit antenna. At the receive antenna, which is located at a distance rt. Yeah. So now the distance relative to the transmit antenna is a function of time. Yeah. And depending on the velocity with which the receiver is moving, this will change with time. So r0 is, for example, the distance of the receiver with respect to the transmitter at time t equals 0. Depending on velocity and time elapsed, the distance will change by this amount. Okay. So the response at the receive antenna will now be what? It will again be a superposition of two components, one that reaches the receiver via the direct path, the other via the reflected path. So this is what 2 pi f t minus rt by c. In place of rt, we have substituted r0 plus vt, and so after some rearrangement, you get this. Yeah, attenuation is a function of the distance traveled along the direct path, which is rt in this case. And then along the reflected path, it travels a distance d plus d minus rt, which is 2d minus r0 minus vt. And then the delay cosine 2 pi ft will be delayed by an amount minus 2d minus r0 by c minus vt. Yeah, so I hope it is clear. So along the direct path, it undergoes a delay of rt by c. Along the reflected path, it undergoes a delay of 2d minus rt by c, or 2d minus r0 minus vt by c. That is what is substituted, and that makes it look, I mean, yeah, look complicated. But all we are doing is signal gets delayed by an amount equal to the distance that it travels divided by the velocity. Now, so what was transmitted? A sinusoid at frequency f was transmitted. What is received has a frequency which is different from f. For example, the first component, the first component, the frequency is translated by an amount minus FV by C. And this is essentially the Doppler shift suffered by the waveform as it travels along the direct path. And we understand that we have a minus sign here because the receiver is moving away from the transmitter. The Doppler shift along the reflected path is plus FV by C, and that's because the receiver is moving towards the wall. Okay. And a parameter called as Doppler spread, which is essentially the difference in the Doppler shift that you encounter when we travel along the two paths, it is 2 FV by C. Yeah, this should have been D2, I mean D1 minus D2 mod. All right, so this is essentially the Doppler spread 1 by 2 TC. Just to give you a feel for numbers again, 900 megahertz receiver moving with 60 kilometers per hour. The Doppler spread is of the order of hertz. Okay, now to visualize the role of Doppler spread, yeah, on the received signal, let us do the following. Let us make the following assumption. Let us assume that the receiver is very close to the wall. Yeah, so let us say that yeah, so let us say that R0 plus Vt is approximately equal to 2D minus R0 minus Vt. Yeah, and this condition will hold. I mean, for this condition to hold good, the receiver has to be very, very close to the wall. Okay, so essentially what we are trying to do is we are trying to approximate this by R0 plus Vt itself, so that we can pull this common factor out and we can write it approximately as alpha by R0 plus Vt times this component minus this component. All right. And we understand this minus sign is because the sign of the electric field is reversed as it hits the reflecting wall. Yeah. So this is an approximation that holds good as long as the receiver is very close to the wall. And we are doing this just to understand that the role that the Doppler spread plays in a scenario where there is relative motion and a reflector present in the environment. Right. So if we simplify this further, yeah, we just need to apply an identity like cos A minus B minus cos A plus B. Yeah, and if we apply that identity, oh, I'm so sorry. We need to apply cosine A minus cosine B. Yeah, and express it in terms of sine of the sum of the two divided by 2, sine of the difference of the two divided by 2. So cos A minus cos B can be written down as the product of two sinusoids, applying that trigonometric identity. Now, how do we interpret this? So what was transmitted from the transmitter antenna was a sinusoid at frequency f. Now, when we are in a scenario where the receiver is mobile, moving with a velocity v away from the transmitter, and there is a reflector present in the environment, what is received at the receive antenna is a product of two sinusoids. The first sinusoid has a frequency fv by c, which is of the order of hertz. And then there is a second sinusoid at frequency f, which is of the order of gigahertz. Yeah. Now the way to visualize this is the system is as follows. Yeah, we clearly understand that the system is no longer time invariant. It varies with time. The channel characteristics, they are varying with time. And then there is an additional Doppler spread that kicks in. What it does to the sinusoid transmitted at input frequency f is that it will generate a response. Yeah, the response will be another sinusoid at f, of the order of gigahertz, but with a slowly varying time envelope at frequency ds by 2. Okay, so that is essentially the effect. Yeah, so the response will be a sinusoid at frequency f, but with a slowly time varying envelope. And the variation of the envelope, if you notice, it depends on the Doppler spread, which in turn depends on the velocity with which the receiver is moving. Okay. So to summarize, what have we discussed so far? We have discussed 4 different toy examples. And these toy examples are, although they are over idealized channel examples, they give us insights or intuition as to how do we basically need to model a wireless channel, For example, we looked at the fixed transmit receive scenario. The channel is an LTI system. Fixed transmitter receiver mobile, or if there is relative motion, it can be the other way around as well. Receiver static, transmitter mobile. The channel will be a linear time varying system. The moment you add in a reflector to static transmit receive pair, what is received at the destination is a superposition of delayed copies of the transmitted signal, and the delay of different copy will depend on the distance that the wave travels along those different paths. Yeah. Even though a reflector is added, if transmitter and receiver they are static, the channel behaves as a linear time invariant system. But the moment you introduce motion, yeah, relative motion between the transmitter and the receiver, yeah, things like Doppler spread show up. Even if you transmit a sinusoid at frequency f, what you receive is another sinusoid at f, but with a slowly time varying envelope. All right. So yeah, but in practice, in a wireless setting, you may involve you may have transmitter and receiver that are both moving at the same time. I mean, there is some relative motion between both the transmitter and the receiver. Or you can look at a scenario where there are multiple reflectors all around. Okay. Now, one approach to model a wireless channel is to get into wave propagation analysis through Maxwell's equations and figure out how the wireless channel actually behaves. But we as engineers, we generally resort to the ray tracing approach, which is again not straightforward. But one thing that we understand is that linearity still holds. Yeah, received signal can still be written down as the sum of the responses from different paths. Okay, this brings me to the next slide, where what we do is we try to develop an input-output model for the wireless channel. All right, so now we are looking at a scenario where there are not necessarily two reflectors. There can be multiple reflectors around the transmitter or the receiver. And when a signal is transmitted, it may reach the receiver via several different physical paths that are statistically independent of each other. For example, the signal can go hit this reflector, reach the receiver. It can go hit this reflector, reach the receiver. And you clearly understand that the signal travels different distances, I mean, different amount of distances as it reaches the receiver. Via this path, it travels a distance this. Via this, it travels a distance equal to this. And we also understand that depending on the distance traveled by a wave, the phase may change. All right. Now, if all these copies add up in phase at the receiver, you get a boost. If they add up out of phase, the received signal grows weaker. Yeah. So depending on how dynamic the environment is, the strength of the channel can change. All right. And that is what we term as multipath fading. Okay. So throughout this lecture, we'll not focus on path loss and shadowing because the focus is more on trying to develop maximum likelihood decision rules and evaluating the error performance. Yeah. So more on so the focus is more on trying to ensure reliable communication over the air, and that is why we'll focus more on discussing the small scale fading aspect of the wireless channel. Path loss and shadowing, they're more useful if we are doing some kind of cell site planning or deciding where to put the base stations. All right. Yeah, but here we are worried about discussing reliable and efficient detection techniques, so we'll focus more on the small scale fading aspect. Now, let us say that the signal x of t, which is again a sinusoid transmitted at frequency f from the transmitter, then the received signal for a generic wireless channel can be written down as what? It can be written down as a weighted linear combination of the delayed replicas of the transmitted signal. All right, that is what we have done. So if you compare it to the two-ray model or the two-path model that we just considered in the toy examples, yeah, in general you can have I different paths. Yeah, you can have several different paths through which the wave travels and reaches the destination. So that is what so this summation captures in fact that, and then there's the weight. Yeah, that captures the overall attenuation of path I between the transmitter and the receiver at time t. Sorry for the typo again, this should have been t. Yeah, so depending on the time snapshot that you are looking at, depending on the time snapshot that you're observing the channel, I mean, the channel characteristics can vary across time. This captures the overall attenuation, and it is a function of transmit-receive antenna radiation patterns. It also is a function of the nature of reflections, whether it is it is also a function of the distance between the transmitter and receiver along path I. Yeah, if you compare it to the two-ray model, we understand that the attenuation, I mean, this is inversely related to the distance traveled. You get different delayed replicas. So tau I ft is the delay associated with path I at time t, and it is a function of distance between the transmitter and the receiver as the wave propagates along path I. Okay, so this is a generic model, yeah, and we can clearly see where it is coming from. Yeah, if you just look at the toy examples, you can easily extend this to a scenario where instead of just a single reflecting wall, you have multiple reflectors around the transmitter and the receiver. All right. Now we will focus on narrowband communication, which essentially means that we'll look at a scenario where the signal is transmitted over a bandwidth W, which is much lower than the carrier frequency. All right. Now, if we look at this particular scenario, then we can get away with the dependence of the attenuation factor and the delay factor on frequency. Yeah, essentially these two factors will be independent of frequency, and the output yt for an arbitrary input x of t fed to a wireless channel, yeah, the input xt has non-zero bandwidth, is given by this. Yeah, so what is the change compared to this? We have dropped the dependence on f, and that is primarily because we are now focused on discussing communication over a narrow band. And narrow band means signal transmitted over bandwidth W, which is much lower than the carrier frequency. Okay, and if this condition is satisfied, then these two factors are roughly independent of frequency f. And the output of the channel or the response at the receive antenna can be written down as the weighted linear combination of the different delayed copies. All right, tau I and ai, I mean the delay and the attenuation factors being independent of frequency. Okay, and from this, so and what will be the linear time varying system? What will be the impulse response of this system? It will be AIT times delta tau minus tau IT. All right. So how do we get this? You can obtain this. So we understand that x of t, when it is fed to a system with impulse response h tau comma t, you obtain y of t, and y of t is the convolution of this with x of t. All right, and that is what. So if you look at the impulse response, what does it give you? It gives you an idea about the strength and the delay associated with different paths. Yeah, AIT gives you the strength of the ith path. Tau IT gives you the delay associated with the ith path. And how is this defined? This is defined as the response at time t due to an impulse applied at t minus tau. Okay. Notice that this is something that varies with time. It captures the effects of mobile users' multiple reflectors. Okay, so this varies with time. What do I mean by that? I mean, depending on the time instant at which you are observing the channel, the number of multipaths can change. The number of reflectors can change. All right, so all that can change. So I mean, the number of turns contributing to the channel, this may change. Yeah? If you take the Fourier transform of this, the time varying frequency response becomes AIT exponential minus j2 pi f tau IT. All right, it is just the Fourier transform of this. Now, so this is the impulse response of a linear time varying system, and we understand. Yeah, so this is different from linear time invariant system, where for a linear time invariant system, if you look at the response of the channel at time tau to an impulse applied to the system at time 0, that will be exactly equal to the response observed at time t due to an impulse applied at t minus tau. All right. So if the channel is time invariant, then the impulse response does not vary with time. If at time instant t equals t naught, you had 3 different paths between the transmitter and the receiver, and each path had a certain delay and attenuation associated with it. If you look at the channel at some other time instant t equals t2, then the number of paths will not change. The attenuation and the delay associated with different paths will not change at all. Okay, so that is linear time invariance. Linear time varying, meaning if you look at the impulse response at, let us say, time instant t1, it may have certain number of paths and attenuation delay associated with every path. If you look at some other time instant, the number of paths itself may change. Yeah, and the attenuation associated or the delay associated with different paths may also change. And that is a scenario which you encounter when you have relative motion between the transmitter and the receiver. Okay, yeah, you can understand that. Let's say your receiver is mobile. Let's say you are sitting in a car and you're moving around. You can clearly understand that your wireless channel is dynamic in that sense. Yeah, the kind of reflectors that you have keeps on changing as you move along, and that is why your impulse response keeps changing as we move away or towards the transmitter or the receiver. Okay, for example, for this particular scenario where we had transmitter and receiver, and there was a wall present in the environment, the receiver was moving with a velocity v away from the transmitter. The response at the receive antenna, yeah, we had written this down. Yeah, so this is the signal received along the direct path. This is the signal received along the reflected path. And yeah, if we try to model it using this system, we clearly understand the attenuation along the direct path is mod alpha by r naught plus vt. Attenuation along the reflected path is mod alpha by 2d minus r naught minus vt. The delay associated with the direct path is r naught plus vt by c minus a certain angle phi 1 that depends on the phase change introduced at the reflector, transmitter, or receiver. And tau t is the phase change associated with the reflected path. And we understand that whenever a signal hits the reflector, sign of electric field is reversed. So phi 2 equals pi, but phi 1 is 0. Yeah, so this is a generic model. Yeah, generic model that captures the effect of mobility between the transmitter and the receiver. It captures the effect of several number of reflectors present in the environment. All right, and any such toy example, yeah, we clearly understand. Yeah, this should have been A2 here. I'll fix these typos before I forward the slides. Yeah. Okay. Now, yeah. So what have we done so far? So this is the continuous time model for the channel. Now, in typical wireless applications, what happens is that communication happens over a passband of bandwidth W. All right, centered around a carrier frequency of FC. All right. However, most of the processing at the transmitter or at the receiver, be it coding, decoding, modulation or demodulation, or be it synchronization, it is usually done in baseband. Baseband meaning the band centered around 0. Yeah, the bandwidth remaining the same, W. All right. So what we have discussed so far was the continuous time passband model. We are, however, interested. See, eventually, what we want to do with we want to characterize the channel, and at the same time, we want to obtain the baseband equivalent so that we can do an error performance analysis. All right, because most of the processing, be it coding, decoding, modulation, demodulation, or synchronization, that's done in the baseband. All right. Now, we know that the input xt and its baseband equivalent, they are related this way. Xt equals real part of xbt ej2 pi fct. All right, I will skip the details here in the interest of time, but if you look at these two, so the goal is to obtain this kind of a spectrum, passband spectrum, from the baseband spectrum. And if we take the Fourier transform of this, and use Fourier transform properties, it can be proved that the input xt and its baseband equivalent, they're related this way. Yeah. Understand that it does, baseband to passband conversion involves some kind of up conversion. Yeah. And when we multiply exponential j2 pi fct, we are up converting the frequency to a higher band, let's say fc. All right. So yeah. I'll not go into the details. Perhaps this was covered during the baseband and passband representation of the signals. Yeah. So understand that XT and its baseband equivalent, they are related this way. Our goal is to obtain the output of the channel in terms of the input in the baseband. All right. So we understand that the output of the wireless channel, it is a linear combination, weighted linear combination of the delayed copies of the transmitted signal. All right, that is what this says. Now, if we just do some mathematics, we plug in the we express this passband signal in terms of its baseband equivalent, then xt minus tau it can be written down as the real part of xbt minus tau it exponential j2 pi fc t minus tau it, and that is what this gives you. Assuming that this attenuation component is real, one can move this real operator outside of the summation, and we can write it this way. Yeah. Now, if we just pull exponential j2 pi fct out, whatever remains is ybt. All right. So essentially, ybt, the baseband equivalent, can be written down in terms of the baseband equivalent of the output, can be written down in terms of the baseband equivalent of the input, albeit with a factor which is AIT exponential minus j2 pi fc tau it. So in the baseband equivalent, we can clearly see that the phase associated with every path, it changes at different rates. Okay. Yeah. So AIBT times XBT minus tau it. AIBT, the phase associated with different path, it changes at different rates depending on tau it. Okay. For example, the phase will change by an amount pi by 2 if tau it changes by 1 by 4 fc. So if tau it, if we plug in 1 by 4 fc here, what do we notice? The phase changes by pi by 2 radians, and that's a big change. That's a massive change. Or in other words, if the path length changes by a small amount, c by 4 fc, this is what? C is generally of the order of 10 power 8. Fc is, let's say, gigahertz, so 10 power 9. So this is roughly 0.1 meter. So even if the path length changes by an amount 0.1 meter, we undergo a change of pi by 2 radians in phase. All right. So this is something that is much more sensitive to changes in delay. All right. This changes rather slowly. Yeah. So what have we done? We have developed the baseband equivalent input-output model, which is AIBT XBT minus tau it. And as before, the equivalent channel impulse response in baseband equals this AIBT delta tau minus tau it. One can take the Fourier transform of this, and that will be the frequency response of the baseband equivalent channel. Yeah, simple. I mean, it's a couple of steps. Yeah, just take the Fourier, apply the definition of Fourier transform, and if we do that, this is what we obtain. We obtain the relation between the baseband equivalent of the frequency response and the passband equivalent of the frequency response. And we can clearly see that there is some up conversion involved. Yeah, the band centered around 0 is up converted to a band centered around FC. Yeah, so that's essentially passband to baseband. Now, so what have we done so far? From passband, we obtained the baseband equivalent of the channel. Yeah, we are now interested in obtaining the discrete time baseband equivalent of the linear time varying channel. So to do that, let us say if XBT is band limited to W by 2, yeah, XBT band limited to W by 2, it means that the Fourier transform of XB2 is essentially 0 beyond W by 2. That is what we mean here. Fourier transform of XBT is 0 beyond W by 2. If this signal is sampled at the rate W, okay, then yeah, invoking sampling theorem, XBT can be written in terms of its samples this way. All right. So this is what? This is essentially the reconstruction equation. What are we trying to do? Given that we have samples of this signal collected at the rate 1 by W. All right. So we have samples. All right. What we want to do is from these discrete time samples, we want to obtain a continuous time function. Yeah. And So we have these samples collected at the rate 1 by W, and we know that this continuous time signal is band limited to W by 2. By passing these discrete time samples through a low pass filter, we know that exact reconstruction is possible. All right. Now, a low pass filter has a flat frequency response. All right. So we understand that it has a frequency response which is flat around 0, and then it transitions from passband to stop band at a certain cutoff frequency. Let's say F cutoff. All right. So now passing these samples through a low pass filter. So a low pass filter has a flat frequency response. So in the time domain, if you look at the impulse response of a low pass filter, it is essentially a sinc function. All right. So in the frequency domain, it amounts to the multiplication of the Fourier transform of these samples, or the sampled version of the signal, with the frequency response of the low pass filter. In the time domain, that corresponds to the convolution, discrete time convolution of the samples and the impulse response of the low pass filter, which is a sinc function. Okay, so see, the way to interpret this mathematical equation is that you have samples. Using this sinc function, you are trying to interpolate between these samples in order to obtain a continuous function xbt. All right, and so this is also called as the reconstruction function or the interpolation function. Yeah, this is an ideal interpolation function. All right, so xbt or xbn, using this sinc function as the interpolation function, one can obtain an ideal reconstruction of the continuous time signal. Or in other words, xbt in terms of its samples, it can be written this way. Now, so all that said and done, if so, the baseband output, we understand that it is aibt xbt minus tau it. Okay. Yeah, we can plug in for xbt in terms of, so we can write down this signal in terms of its samples this way. Now, since this is a linear time varying system, we understand that there will be Doppler spread involved. Yeah, and therefore the bandwidth of the output will be slightly larger than the bandwidth of the input. However, we understand that the Doppler spread is generally of the order of hertz, and bandwidth is generally of the order of megahertz. So we ignore this effect of Doppler spread, and we sample the output, let us say, at the same rate W. So YBM is the sample of YBT obtained at the time instant M by W. So if we do that, so basically sample the continuous time output at the rate 1 by W. In order to obtain the mth sample, let us say we sample at t equals M by W, we'll get this. Okay, some mathematics. Yeah, one can simplify this discrete time baseband output as follows. So YBM can be written down as the convolution of the discrete time baseband channel impulse response and the input discrete time samples. Yeah. Now this HBML is the lth tap of the channel at the mth time instant. Okay, and it is given by this crazy function here. Okay, we'll see how to interpret this function just yeah, in a moment. Okay, so so this is the lth tap of the channel at the mth time instant. It will be clear what I mean by tap in a moment. Okay, so the lth tap of the channel at the mth time instant is given by this. Now, what I want to convey is the following. The lth tap, so there can be 100 different physical paths through which a signal can travel and reach the receiver, but there will be few paths that reach the receiver roughly at the same time. Okay, so all such paths along which the signal is received at the destination at very close spacing in time, they constitute a tap. Yeah, so the lth tap is essentially an aggregation of a large number of statistically independent paths over a small time window. Okay, so what I mean, sorry, I'm scrolling through the slides, but I want you to, yeah, so for example, these three, I mean, the signal via these three paths may reach the receiver at roughly the same time, because the signal may travel approximately the same distance as it hits these three reflectors. Now, if these three copies are received at the same time, a very close spacing in time or in a small time window, these three paths can be roughly classified as a tap. Yeah. So basically, if you receive copies from a reflector cluster at the receiver, you can classify all those physical paths, although they come from independent reflectors, they can be classified as a tap. And this can be classified as one tap, this can be classified as the other tap. All right, so that is what tap essentially means. Okay, so we understand that the lth tap of the channel at a certain time instant is the aggregation of a large number of statistically independent paths. And if you look at the mathematics here, with every path that contributes to the lth tap, there is a phase term associated. Yeah, fc tau I m by w. Yeah, so tau I is what? The delay along the ith path, and tau I equals distance traveled along the ith path divided by the velocity c. Fc by c gives you a lambda. So essentially this is equal to e minus j 2 pi di by lambda. Now, depending on how big your di is relative to the wavelength of the signal, the phase can vary uniformly between 0 to 2 pi. All right. Moreover, the phase of different paths that contribute to the lth tap can be independent. Okay, so attenuation that a signal undergoes when it travels along the ith path is also random, and again that can is also random and independent along every path. Yeah. So what are we looking at? We are essentially looking at the sum of a large number of independent random variables. All right. And if we invoke central limit theorem, yeah, we can obtain the statistical characterization for the discrete time baseband channel. Yeah, so the lth tap of the discrete time channel at the mth time instant is essentially the sum of a large number of independent random variables. And by central limit theorem, the lth tap can be modeled as a complex Gaussian random variable. Okay. Mathematically, this is how we write it as HBML is complex Gaussian with mean 0 and variance sigma L square. And this is essentially the small scale fading model. One can notice that the variance may be different for different L because I mean, different paths may contribute to different taps. Yeah, so that is what we mean by variance being different for different L. This can also vary with time. Yeah, we see that there is an index M associated with it. So accordingly, it can be time varying. Now, just a fact, this can be proved. Yeah. In the interest of time, I'm not discussing the proof. If this HBML is complex Gaussian mean 0 variance sigma square, one can show that its envelope or its magnitude will be Rayleigh distributed, and its mod squared will be exponential distributed. And this is where the small scale fading component derives its name. Yeah. When we talk about Rayleigh fading, what we essentially mean is that the underlying wireless channel coefficients, they are Gaussian distributed, and they're Gaussian distributed because we understand that the lth tap is basically an aggregation of a large number of statistically independent paths, large number of paths through which the signal can travel and reach the destination. Yeah, and therefore we can model this as a Gaussian random variable, and its envelope can be modeled as Rayleigh, and that is why fading, small scale fading, is broadly Rayleigh fading. There's an alternative model for discrete time baseband channel. Yeah, I'm actually hurrying up because I'm short of time. So the lth tap of the channel at the mth time instant, it can be modeled this way. Yeah, where there is a line of sight component attached, yeah, to the Rayleigh fading part. Yeah, this is also called as a specular path, and this is the scattered path. Now, if you notice, this random variable no longer is 0 mean. It has, so this is the deterministic path. Sigma L is deterministic. EJ theta, theta is the angle of arrival. This is again deterministic. So if you compute the mean of this random variable, it will turn out to be non-zero, and let's call it mu. Yeah. So if you look at the magnitude or the envelope of this non-zero mean complex Gaussian random variable, it is right-shaped. Okay. K is the Riccian factor that captures the ratio of energy contained in the specular path to the energy contained in the scattered paths. And if you notice, for K very, very large, yeah, this component essentially reduces to 0, and you're left with the deterministic component. The moment K goes to 0, you're left with the Rayleigh fading component. All right. I mean, you're left with 0 mean Gaussian random variable whose envelope is Rayleigh in nature. So understand that the envelope of a 0 mean Gaussian random variable is Rayleigh. That of a non-zero mean Gaussian random variable is Riccian. Okay. there are several different characteristics that can be defined for a wireless channel depending on these parameters. If the coherence time of the channel is much larger than the transmit frame duration or the coding block duration, then we say that the channel is slowly fading. If the coherence time of the channel is much smaller than the transmit frame duration, then we say that the channel is fast fading. Yeah, under fast fading, different symbols in a frame may see different channel realizations. Okay. Then there's something called as flat fading. Under flat fading, the signal is transmitted over a bandwidth which is much lower than the coherence bandwidth of the channel, or the delay spread is much smaller than the symbol duration. And if this happens, you are essentially looking at a channel with a single tap. All right. Frequency selective fading, if the coherence bandwidth is much smaller than the bandwidth over which the signal is transmitted, then the signal undergoes frequency selective fading. Signal at different frequencies will undergo different amounts of attenuation and phase shift. All right, and if you look at this particular phenomenon in the time domain, the delay spread is much larger than the symbol duration, and essentially what you have is a channel with multiple taps. Okay, this brings me to the end of part 1. I'll quickly take you through the key points. So Firoza, I'm sorry, how much time do I have really?
So the next session is scheduled from 12:30, sir, but you can take session like if required.
Okay, yeah, since I started,
we can extend it, sir, little bit.
Since I started roughly 15 minutes later, so I'll just take 15 more minutes to continue.
Yeah, sure. We will inform Ratnajit, sir.
Yeah. Okay. So digital.
Thank you, sir.
Yeah, thank you. So part 2 of the talk now focuses on digital communication over fading channel. All right. So again, we will take several examples to understand how digital communication really happens over fading channel and how is it different from digital communication over AWGN channel. All right. So the first example we'll take is that of a non-coherent receiver. Okay. So let me first set up the model and then we'll try to analyze this. Okay. So what we consider is the following. Let us say that the signal received at the mth time instant equals ym, and this is equal to hm times xm plus wm. Okay. What are we looking at? We are looking at a discrete time single tap channel. Okay. Single tap hm. And when does the wireless channel? When is it that the channel has a single tap? Channel has a single tap if the delay spread is much smaller than the symbol duration of the much smaller than the symbol duration. All right, then the wireless channel essentially is a single tap channel. All physical, I mean, there can be multiple paths through which the signal reaches the receiver, but all those paths reach within a window which is much lower than the symbol duration. All right, and that is why the channel is a single tap. So ym equals hm xm plus wm. We are looking at a single tap channel. hm is complex Gaussian mean 0 variance 1, and the noise at the receiver is complex Gaussian mean 0 variance sigma square. Now we are looking at a setting where the receiver is non-coherent, meaning the receiver has no clue about the instantaneous value of this wireless channel coefficient hm. Okay. Now we are looking at a transmission scenario where we are doing orthogonal signaling. Now under orthogonal signaling over 2 time samples, let us say m equals 0 and m equals 1, either symbol A, which is xa equals a0 is transmitted, or symbol B, which is xb equals 0a is transmitted. Okay. So what this means is that if xa is transmitted, then over time sample 0, A is transmitted, time sample 1, 0 is transmitted. If symbol B is transmitted, then at time instant 0, you transmit a 0, time instant 1, you transmit an E. Okay. So what is the setup? We are looking at orthogonal signaling over 2 time samples over a single tap channel. All right. In a scenario where the receiver has no information about the channel. All right. Receiver has no knowledge of the channel. What is the objective? The objective is to, so based on the Y that is observed at the destination or at the receiver, the goal is to figure out whether XA was transmitted or XB was transmitted. All right. So this is common to any receiver design problem. At the destination, we are interested in figuring out what was transmitted among the various possible alternatives that are available. All right. So here, I mean, the transmit symbol, we are considering transmission over 2 time samples, and either A0 can be transmitted or 0A can be transmitted. And note that these 2 signaling points, they are orthogonal to each other. Now, if X equals XA is transmitted, yeah, what is XA? XA is A comma 0, which means at time instant 0, you transmit an A, and that will be multiplied with the channel coefficient at time instant 0 plus W0. Yeah, this is the received sample at 0th time instant. The symbol at the first time instant received will be, since a 0 is transmitted, so 0 multiplied with H1 plus W1. Now, given that X equals XA is transmitted, the received symbol at the 0th time instant is complex Gaussian. The mean is still 0 because H0 and W0 both are 0 mean. The variance will be A squared times the variance of H0 plus the variance of W0, which is A squared plus sigma squared. Similarly, the variance of Y1 will be sigma squared. All right, and it is still 0 mean. So given that X equals XA is transmitted, the symbol received at the 0th time instant is complex Gaussian mean 0 variance A square plus sigma square. And Y1 is complex Gaussian mean 0 variance sigma square. And moreover, these 2 are independent. These 2 time samples are independent of each other. On the contrary, if X equals XB is transmitted, one can figure out that Y0 is Cn0 sigma square and Y1 is Cn0 A square plus sigma square. And as before, Y0 and Y1, they are independent of each other. Okay, so now we don't really have, H known at the receiver, but what we have exploited here is the fact that the statistics of H is known. Yeah, it is known that H is Cn01. Okay, so given that X equals XA is transmitted, these 2 time samples have statistics given by these, and these 2 have statistics given by these. Now, if we write down the maximum likelihood decision rule, note that ML rule is same as maximum a posteriori rule, provided the symbols that you transmit are equiprobable. Yeah, so we'll straight away start with maximum likelihood decision rule. And so at the receiver, you decide in favor of XA being transmitted if the conditional probability density function of the vector Y given XA is larger than the conditional PDF of the vector Y given XB. All right. Now, given XA, Y0 and Y1 are independent of each other. So you can write this down as the conditional PDF of Y0 given XA times the conditional PDF of Y1 given XA. And on the right hand side, you will have conditional PDF of Y0 given XB times the conditional PDF of Y1 given XB. All right. Yeah, so now we understand that given XA, Y0 is Cn0 A square plus sigma square. Given XA, Y1 is complex Gaussian with mean 0 and variance sigma square. Yeah, so that is basically the Gaussian PDF with mean 0, variance A square plus sigma square. This is the Gaussian PDF with mean 0 and variance sigma square. Given that XP is transmitted, Y0 is complex Gaussian mean 0, variance sigma square. Yeah, so mean is 0, variance is sigma square. And Y1 is complex Gaussian with mean 0 and variance A square plus sigma square. Yeah, a little bit of mathematics, so it can be further simplified. And it can be reduced to this optimal ML rule, which essentially says that at the receiver, you decide in favor of symbol A being transmitted if the energy of the received symbol over the 0th time instant is larger than the energy of the received symbol over the first time instant. Yeah, you cannot do anything better than this, primarily because you don't really know H at the receiver. Yeah, so we can notice that this rule does not make use of the phases of the received signal. And that is essentially because we don't really know the phases of H0 and H1, and we cannot use them for detection. Okay, so this is the optimal ML rule for a receiver that is non-coherent, that does not know anything about H. if we, based on this ML rule, if we do the error performance analysis, probability of error by symmetry can be written as probability of error given x equals xa. Now, given that x equals xa is transmitted, the receiver will make an erroneous decision if the receive energy over the first time symbol is larger than the receive energy over the 0th time instant. All right. So we are interested in computing the probability of this event. Call this as Z1 and this as Z0. So we are interested in finding out probability that Z1 is greater than Z0 given x equals A. Note that Z1 equals Y1 mod square is independent of Z0 equals Y0 mod square given that x equals XA is transmitted. All right. And since this is Gaussian, Y1 and Y0, they're Gaussian. We already know the statistics. Given XA is transmitted, their mod square values will be exponential distributed. All right. So one can basically write down the joint PDF of Z0, Z1 and integrate over the corresponding decision regions, Z0 to infinity, 0 to infinity. This joint PDF can be written down as the product of the marginal conditional PDFs. Okay, now given x equals xa is transmitted, this is 0 mean sigma square. So Z1 will be exponential distributed with parameter sigma square. And given x equals xa is transmitted, Z0 will be exponential distributed with parameter a square plus sigma square. So what we have done is we have written down the exponential PDF here. And if we further simplify this, we get it as 1 by 2 times 1 plus SNR, where SNR equals the average symbol energy per time instant divided by the noise energy per time instant. So a square by 2 divided by sigma square. All right. So what do we notice? So a couple of remarks. When we do orthogonal signaling over flat fading in a non-coherent receiver, so at high SNRs, one can notice that error decays as 1 by 2 SNR. All right. In order to get an error probability of 10 power minus 3, one would require an SNR of roughly 500, which is 27 dB. Okay. If we compare this to the binary signaling or the antipodal signaling over additive wide Gaussian noise channel, yeah, one can do similar steps for an AWGN channel and can figure out that the probability of error can be written down in terms of Q function. It is Q of root 2 times SNR. Yeah, and Q of x, Q function can be upper bounded by an exponential. So Q of x is less than equal to exponential minus x square for x large. Yeah, so therefore at high SNRs, when we do antipodal signaling or binary signaling over an AWGN channel, the error rate, it decays exponentially with SNR. Yeah. So over an AWGN channel, in order to get an error probability of 10 power minus 3, one would require an SNR of roughly 7 dB. Yeah, you can clearly see that over flat fading relay channels, the decay in error probability is much slower with SNR. Yeah. Yeah, you can clearly see that you require 20 dB more SNR in order to obtain the same target bit error rate over a relay flat fading channel. Yeah, when compared against an AWGN channel. Here the decay is exponential. Here the decay is linear. Yeah, the slope. SNR power minus 1. Error decays as SNR power minus 1. Here the error decays as exponential SNR. Much faster decay, slower decay. Yeah. So fading really, spoils the performance. When we talk about coherent receiver design, this is particularly the case when, let us say, H is known at the receiver. Yeah, and let us say XM can be either plus A or minus A is transmitted. As before, we consider a single tap channel. And since in order to decide on what was transmitted at the mth time instant, we only need to use the symbol received at the mth time instant. We can drop the index M. And so the model essentially reduces to Y equals HX plus W. As before, receiver design, what does it involve? Based on Y, we need to figure out whether X equals plus A was transmitted or X equals minus A was transmitted. One can write down the ML decision rule. If this conditional PDF Y given X equals A is larger than Y given X equals minus A, at the receiver, we decide in favor of A, else we decide in favor of minus A. All right. Now, Y given X equals A is transmitted. Y given X equals A is transmitted is complex Gaussian, but with mean value A times H, and the variance is sigma square. Yeah, so that is what we have done. So given that X equals A is transmitted and H is known at the receiver, this is essentially complex Gaussian with mean value HA and variance sigma square. Otherwise, it is complex Gaussian with mean value minus AH and variance sigma square. Yeah, this essentially reduces to the following distance rule, minimum distance rule. Yeah, I mean, for this to be larger, the argument has to be smaller. Yeah, so that is why you can see a flip in the inequality here. If this is smaller, then you decide in favor of A, else you decide in favor of minus A. Now, these are all complex numbers. You expand this, we can write it as y mod square plus h mod square A square minus 2 times real part of h star y A. Yeah, and the so basically, if we further simplify this, the optimal decision rule comes out as you decide in favor of A if the real part of h star y projected in the direction of h comes out to be greater than 0, else you decide in favor of minus A. One can again do a series of steps and figure out the error performance conditioned on h. Yeah, the receiver will make an erroneous decision if given that x equals A is transmitted, if the real part of h star y is less than 0, then it makes an erroneous decision, and this is what constitutes the error event. If we do a series of steps, one can figure out that probability of error conditioned on h will turn out to be √2 alpha times SNR. Now, given and in order to derive this, we have used the following fact: h star w, given that h is known, will be Cn0 sigma square h mod square. And the real part of this will be mean 0, but the variance will reduce by a factor of 2. Yeah, if h is Cn01, its mod square will be exponential 1, exponentially distributed with parameter 1. And therefore, the average error performance, if we do a few steps, it comes out as half times root SNR by 1 plus SNR. Now, at high SNRs, all we have to do is use binomial expansion and reduce ignore the higher order terms. We'll notice that probability of error is approximately equal to 1 by 4 SNR, right? So what really happens, in order to get an error probability of 10 power minus 3, one would require an SNR of 250, which is 24 dB. So although we obtain a 3 dB gain in SNR relative to the case when the channel knowledge is not available at the receiver, we are still far off from the AWGN channel. Yeah, the error probability still decays as SNR power minus 1. All right, and trying to design reliable and efficient schemes in wireless communications essentially means trying to improve the exponent of SNR. Yeah, we are always interested in trying to increase the rate of decay of the error probability as a function of SNR. Yeah, and get it as close as possible to the AWGN channel. In the AWGN channel, we understand that error rate decays exponentially with SNR. In the fading channels, we understand that it decays SNR raised to the power minus 1. Okay, if you have a knowledge of channel coefficients at the receiver, you obtain a 3 dB gain, but that is still not sufficient. Yeah, the poor detection performance in fading channel is not. So therefore, we realize that the poor detection performance in fading channel is not due to the lack of knowledge of channel. It is due to the random nature of channel. Yeah, there's a significant probability that this instantaneous receive SNR goes below 1. Yeah, so this is the probability of a deep fade. Yeah, the probability that your channel is very, very bad. Yeah, and we can clearly see that this also decays inversely with SNR. Okay. So what is it that spoils the performance in relay fading? It is the likelihood that the channel can go in deep fade. Yeah, and the probability of that is same as the probability of the error itself. Yeah, order of magnitude is the same. So understand that in AWGN channel, it is just the noise that introduces error in transmission. In relay fading channel, you have an additional event kicking in. Yeah, the channel itself can go in deep fade, and that may spoil the performance. That essentially spoils the performance. All right. So there are several techniques, diversity techniques, where instead of just obtaining one observation at the receiver in order to decide in favor of what symbol was transmitted, one can do repetition coding. Basically, transmit the same symbol at different time instants. And then based on a vector of observations, you decide in favor of what was transmitted. Now, depending on how many times you repeat the same symbol, you can obtain a decay in the error rate. All right, proportional to, I mean, the rate of decay would increase. Yeah, it will be SNR raised to the power minus L if you repeat the same symbol L times. And that is some form of time diversity. But it has its disadvantage because you send the same transmit symbol L times, you take a hit in rate. yeah, your rate becomes 1 by L because you are transmitting the same symbol L times. So one symbol in L channel uses. There's something called as receive diversity, where you have L receive antennas and you transmit a symbol X from a single transmit antenna. Then at the receiver, you get L different copies. Based on those L copies, you try to figure out what was transmitted. Now, the chance that all L links will go into simultaneous fade is much, much lower than the probability of a single link going into deep fade. Okay, so that again brings you an improvement in SNR. All right, so I think that portion will be covered when my colleague talks about diversity in wireless systems. So I leave that discussion for there, but understand that in fading channels, error performance takes a hit, and that is essentially because there is a significant probability that the channel may go in deep fade. Okay, knowledge of channel coefficients does help, but it only gives you a 3 dB gain. Okay, so in order to improve the rate of decay, so all the wireless transmission schemes, they worry about increasing the rate of decay of error probability as a function of SNR, and that is where diversity techniques kick in, and they give you an improved performance. Okay, so this is all I had to talk about, and these are the two classic textbooks on wireless communications, one by David Shea, Pramod Vishwanath, and the other by Andrea Goldsmith. Yeah. You can read these books for further understanding of the topic. All right. Thank you. I can take up any questions if you have.
Thank you, sir.
We have two questions from the participants. So the first question is, in what condition impulse response has to be applied for a system?
Hey, am I? Yeah. Okay.
Sir, in the Q&A section, there is no question. I think so. Pabali, there is no question in the Q&A section, right?
There are two questions are there.
Okay.
The first question is, at what condition impulse response has to be applied
Hey,
for
sorry, I cannot hear you.
So at what condition impulse response has to be applied for a system?
At what condition?
Impulse response has to be applied for a system.
No, see, impulse response, it characterizes a system. It gives you an idea about the kind of amplitude changes and the phase attenuation that a signal, when it is transmitted over the system, undergoes. Okay, so yeah, impulse response by definition is the response of a system when an impulse signal is applied to it. All right, and it gives you an idea about the amplitude and the phase changes that the signal will undergo when it passes through the system. All right, it is a characteristic of the system itself. Yeah, so it defines a system. The frequency response of the system depends on the impulse response of the system. Okay, it is like a signature for a system. Okay.
Shalil, can I come in?
Yes, sir. Yes.
So the idea of modeling is considering it is a LTI type of system, and you know that any arbitrary input, it can be, if you know the impulse response of a system, and for any arbitrary input, now you can actually convolve and get the response of the system for that arbitrary input. Am I correct?
Yes. 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 Yes.
So that is the main idea of going for the impulse response of the system.
Okay, thank you, sir. Sir, so there are no more questions, sir, in the Q&A section. So, Shalil, sir? Yeah.
Fine. I will unshare now.
Yeah. Thank
Thanks,
you, sir.
thanks, Shalil, for joining this. And I was listening to your talk. I was also refreshing myself. Wonderful talk. Thank you.
Yeah. Thank you. Thank you.
Thank you, sir.
Thank you. Thank you. Thank you, sir. Yeah, I'll
Dear participant, so we have ended the second session for day 2. So we are starting with the third session. The third session is being delivered by Professor Ratnajit Bhattacharya, sir. So I would like to request sir to please, sir, we may start the session, sir.
Yeah, good afternoon, everybody. Can you hear me properly?
Yes, sir, we can hear you, sir.
So considering the bandwidth issues, I will keep the video off. I will just share my slides.
Okay, thank you, sir.
Thank you. Is my screen visible to you?
Yes, sir, the screen is visible.
Yeah, so good afternoon, everybody. So we start this third session, and I was listening to the later part of Dr. Shil's presentation. So how we transmit symbols through AWGN channel, how we transmit symbols to fading channel, how the channel actually it distorts the signal, and that's why we get error, what we call the a performance of the communication system. It is the average bit error, and he was showing that if you want to get a bit error performance of roughly 10 to the power minus 3 of that order in a fading channel, you require the SNR to be very, very high. So the mathematical analysis for the communication system, how to find out the bit error rate, these things have already been discussed. I'm going to discuss something which is slightly different and very, very important in the design of practical communication systems. You see that your source of information at the transmitter is at one place, and it is using one set of circuitry for generating the signal, transmitting the signal. Your receiver, which is actually has to receive that signal and from there retrieve the information, it is sitting at another place, and there is some delay or distance associated with it. It is using different set of circuitries. So maybe the carrier frequency we are talking of at the transmitter, it is generated by one circuit. The carrier frequencies you talk at the receiver, it is being generated by another circuit. So how the entire system works? So it is very, very important that we do some sort of synchronization or devise some mechanisms for which the information retrieval becomes as much as possible independent of these issues. So the contents that I intend to cover in this lecture, it will be a very brief lecture because I cannot go into very deep into the details of these things. These are mathematically very, very involved. I will just give you an overview and restrict myself to the block diagrammatic level description without really going into deriving the equations. So need for carrier and symbol synchronization. I'll discuss why it is really needed. And then we'll talk of one particular element which is plays a crucial role in many of the communication systems. It is a PLL, phase lock loop. And then we'll see with some example, for example, how we can do the carrier recovery for BPSK. Professor Shanil was talking of synchronous demodulation, and when you try to demodulate synchronously, you require the carrier at the receiver end. How you get this carrier? You are transmitting the information bearing signal. How you generate this carrier locally? What happens if there is a phase difference between these two? What happens if there is a frequency difference between the generated carrier and the carrier which was used in the transmitter? So these are all important practical issues. And when people design communication system, people normally struggle how to address these issues. And people have come up with a lot of solutions also. Some of the solutions are quite old, and these have been modified and applied to present day communication systems as well. So we'll discuss about squaring loop and Costas loop. These are quite old concepts, but till now very relevant. Then we will talk of a symbol synchronizer in the form of a early late gate synchronizer. And there are many other synchronizers, many schemes are available, but this is the one possibly will give you the basic understanding of requirement of synchronization. That's why I'll pick it up as an example. Also, during this presentation, I will demonstrate you what are the effects if you do not have the carrier synchronization done, and how the synchronization circuitry can actually help in improving your bit error rate performances. So this is the entire plan for spending this approximately 1 hour of time with this. You are free to interrupt me. You can post your queries, or if our E&ICT people allow, you can just ask them. If you have any question, we can interact also directly. You can stop me, you post your questions and ask them to so that we can discuss immediately. So symbol synchronization, this is required for digital communication system which transmit information synchronously. What is happening? We are transmitting a sequence of bits or symbols, whatever we say, and each has some starting time, some duration, and these are to be known properly at the receiver. And not only that, it is to be maintained also at the receiver, because once synchronized, many of the systems actually send some of the practical systems, some of the pilots or synchronizing bit. Once it is synchronized, it should maintain that synchronization as long as the frame of the containing the bits and the symbols are actually received and demodulated and decoded. So carrier recovery is required if the detection is done coherently. For example, very simple example, if you take a BPSK modulated scheme, it will be of the form some BT, where BT is plus minus 1, and cos, say, cos 2 pi FCT. This will be the form of the signal. Now, at the receiver, when you are generating the signal locally, this carrier, if you generate cos 2 pi FCT plus some phi, and then when you try to demodulate the signal by multiplying, as we do normally in the case of DSBC signal, and then you do filtering, then you will get BT multiplied by some cos of phi, and depending upon the value of that phi, you will get the signal strength reduced, and if phi is 90 degree, you will not get any signal at all. So these are the importance of recovering the carrier. Actually, you try to recover the same carrier which was transmitted, which was used during the modulation process in the transmitter. At the physical layer level, the receiver needs to estimate 3 parameters. So these 3 parameters, and please try to look at this word, it needs to estimate. So the theoretical concepts of estimation theory actually comes here, because you are seeing something, you are receiving something, from there you are trying to estimate what was actually transmitted. So this problem is formulated in that manner, and 3 parameters which are very, very important. The incoming carrier frequency FC, any phase shift or phase drift theta t introduced during transmission. As I told that the transmitter and the receiver, they are separated from one another, and any physical signal will take some time to travel. Although this traveling speed is very fast, it travels in the order of that of speed of light, but still when the transmitter and receivers, they are separated by a long distance, because you cannot think of always short distance communication. For example, when you are talking of a satellite type of communication system, your signal is traversing some 65,000 kilometers. So in general, there will be a delay which may be small when your distance is very small, but it will be quite large when you consider the distance to be very, very large. And when we talk of this small delay or large delay, we generally talk in terms of with respect to the bit or symbol duration, how large it is. So any phase shift which is introduced, now any delay will actually, will see it will translate into a phase shift during the transmission, and also the timing, the beat and symbol timing. In fact, where the boundaries, where the symbol starts, when to sample the symbol at the output of the demodulator. So these are the questions you need to answer when you try to build a communication system. And if you are using, say, frame-based transmission, then you will have to have a block level synchronization, starting of the frame. And for that, you see that many a times in communication system, we send some synchronizing bit or preambles and all these things, so that the transmitter receiver come in sync first, and then you send your information. So synchronization and carrier estimation, these are very, very important tasks in practical systems, be it wired system, wireless system, any digital communication system, it is very much needed. In a digital communication system, the output of the demodulator is sampled periodically, and it is sampled once per symbol interval. Now, propagation delay from the transmitter to receiver is generally not known to the receiver. So this is an important thing, because this propagation delay, whatever small delay it is occurring, it is not known to the receiver. Symbol timing must be derived from the received signal in order to synchronously sample the output of the demodulator. And if you consider, I will use very less mathematics just to give you some idea, some essence of the problem. Suppose RT is the received signal and it is ST t minus tau plus nt, where this st, I think already Shalil and all, they have introduced the concept of complex baseband representation. Your st is some real part of some complex baseband signal SLT e to the power j2 pi fct. And then if you introduce a delay of tau, then you can write RT as real part of SLT minus tau. Then this terms come e to the power j phi. This will actually, when you put t minus tau here, you will get a term e to the power minus j2 pi fct, that we are writing as e to the power j phi. And then this is the baseband form of the noise and e to the power j2 pi fct. And this phi is minus 2 pi fc tau, and it is a function of both. Please note that this phase is a function of both frequency fc. Frequency fc itself may change, because when in a practical system you are generating the signal using oscillators, the oscillator frequency itself may change, it may drift. So it is a function of fc and also the time delayed tau. In general, although tau is very small, as I told, in most of the cases when the distance is short, tau will be very small. Phi may be large, because fc is very, very large. Wireless communication, Sholil was discussing, your fc will be in the in terms of gigahertz. So the product fc tau, and that product may be quite large, and the angle phi, that's why, may not be always very, very small. Carrier signal generated at the receiver is not synchronous with the carrier used at the transmitter. I have already told that. And drifts in oscillator are to be taken into account. So most of the practical system, the carrier signal is generated by the oscillator, which the frequency drifts with time, changes in ambient condition. So slowly it changes. So this type of concerns also are to be addressed, so that the system can take up or absorb these small changes and work properly. So the concepts involved in synchronization and carrier recovery will be illustrating using two basic circuits. And be assured, I'll just give you the block diagram of the circuit. I will not go into the actual implementation of the circuit and the mathematical analysis, because this will take lot of time. I'll just block level ideas so that you get a feeling of what we are doing. And I'll tell you about the books later, which you can consult if you want to really want to dig deeper into these topics. So one is the phase lock loop, PLL, for FC and theta C estimation, and the other is the early late gate synchronizer, a simple circuit for symbol timing, that when to sample the output of the demodulator. So we will illustrate or discuss with this simple circuitry. We'll try to understand the concept. So PLL is a circuit that locks into the frequency of the received sinusoid, and V cos omega t theta, and estimates the phase of theta. Please, again, we are using the term estimates. So better is the estimation, less will be the amount of error, but still there will be small amount of error because the PLL itself works on the error. It's a feedback loop and it tries to minimize the error. So there will be very, very small amount of error, but will be very close to the actual frequency and phase. So we have some input signal xt, which can be of the form v cos omega ct plus theta, and it goes to a phase detector, and we have a voltage control oscillator. This voltage control oscillator generates another signal, and this phase detector essentially inside there is a multiplier and followed by a low pass filter, and then this multiplier output, you discard the higher frequencies, it is given to another filter which is a loop filter, which need to be designed, its order, its parameters are to be put accordingly, and then it works on this phase detector output and then feeds to the VCO and controls the VCO output in terms of its frequency and phase. And this VCO generates the estimate for omega c and theta. So there are the analysis, if you want to do performance of these circuits, it takes lot of efforts. So sometimes we go for linearized model. So I'm not going into this. We will use this type of VCOs in our system, and we say that we can make this estimate of omega c and theta quite accurately, and this circuit can be designed to do this job. So a squaring loop is a non-decision directed loop. So these are again decision directed, non-decision directed. So these are the terminologies used, whether you are using the earlier decision of the symbol to modify the estimates. So these issues are there, and it is widely used in practice to establish the carrier phase of double sideband suppressed carrier signals. So DSP signals, you do not send the carrier separately. If it is a AM signal, you transmit the carrier and your PLL, or you can latch on this to this carrier quickly. But for example, when you transmit BPSK type of signal, I'm just taking an example, you have a stream, say BT, which is +1 or -1, and you multiply it with a carrier. So you transmit either cos omega ct or minus cos omega ct. Now this type of signal, this is called DSB-SC, double sideband suppressed carrier. You are transmitting both the sidebands but not the carrier, and therefore you require, if you want to regenerate the carrier at the receiver for synchronous detection, then what you will have to do, you can use some specialized circuitry. A squaring loop is such circuit. So ST is the received signal which is sent to a square law device, and ST is of course of the form, as I told, some BT cos 2 pi FCT plus some phi of this form. Then it goes to a band pass filter which is tuned at 2 FC, and then output will be of this form, and then you have a VCO which generates the local version of the signal, and then you take the product of this, and then the error signal you give to the loop filter and control the VCO output, and finally when the VCO and the incoming signal frequency and phase, they become very close to each other. It goes through a frequency divider, and then you get sine 2 pi FCT, the output of the VCO. So this type of circuits are available, and some of us, we make use of it in our laboratories as well. Many of the undergrad practical classes, we use the VCOs even for FM, sorry, PLLs, even for FM demodulation. So the same PLL we are describing here, and we get an estimate, and you can see that's why we have kept here this hat, phi hat, which is an estimate of the phase. And then once you have this estimate generated, you can pass it through a phase shifter, 90-degree phase shifter as FC, which will give you cos. And then if your received signal is a BPSK signal, and then you can give it to the BPSK demodulator and demodulate the signal. I've given you the reference at the bottom, which is an excellent book, particularly for the digital communication systems. It is not a very advanced level book. It is first course type of books and covers these basics very well. For example, if you want to extend this concept to a fourth power synchronizer for carrier recovery of QPSK signals, then instead of squaring, you raise it to the power of 4, and then you will have this 8 FC filter, then you will have the loop filter VCO, and then divide by 4, and then you will get the in phase and quadrature components, that means sine and cos, both the carriers, that is needed for demodulation of the QPSK type of signal. So you can actually extend this to MPSK, these concepts, but it becomes increasingly more difficult practically to realize this type of systems. At high frequencies, difficulty is encountered in circuit implementation of synchronizers having the squaring or fourth power block, this type of block if you have. So another solution exists, which is called a Costas loop. And here you can see that you have the VCO, then you have the loop filter, and you generate sine 2 pi FCT plus phi cap and 90-degree phase shifter and cos 2 pi FCT phi cap, pass it through the low pass filters, and incoming signal is multiplied here also, and the VCO, it's a feedback loop, and VCO will try to produce the estimate of the carrier frequency and the phase of the received signal. So this Costas loop is also very, very popular in implementing the carrier phase estimation or carrier frequency extraction, generating the carrier at the receiver through this local VCO. I'll take a small break here, and I will go to a demonstration in MATLAB. So in Simulink, I have set up a particular model which gives you how this is my screen visible. I have changed the screen. Hello.
Hello. Yes, sir.
Is my screen visible? I have changed the screen.
Yes, sir. It is visible, sir.
Yeah. So I've set up a simple demonstration where you can see the effect of this carrier and frequency and phase offset, how they actually affect the uh, at the receiver, and also how you can correct them. So here you can see we have a random integer generator, and then we have a QPSK modulator. QPSK, you know, it will transmit two symbols at a time. So our random integer generator, it will be MRE4. It will generate 0, 1, 2, and 3. And then I'm passing it through an AWGN channel. Shalil was discussing some time back. And here I have put EB by N not 10 dB, and Shalil told that you will get very less VER if your EB by N naught is 10 dB. But let us see what happens when we have the phase error or the frequency offset is there in the signal. Now, this is a block where we are introducing a frequency and phase offset to the input signal. For example, I have given a phase offset of 22 degree and frequency offset of 10 hertz. And then we have two chains. One is I'm giving this directly to a QPSK demodulator, and I am doing the error rate calculation, and I will also display the constellation. Another block, it is the carrier synchronizer. Now here you can see QPSK modulation, modulation phase offset, samples per symbol, how much is the damping factor, and normalized loop bandwidth. All those parameters need to be set properly. And then in this case also we are looking into the error that we are encountering. So we expect that since here we are introducing these phase and frequency errors, we expect more error when there is no compensation, and we expect the error to be less when we are doing synchronization. And let's see, let me run this. Seeing is believing. So you can see here the left hand side, this is the constellation diagram after restoration, and it looks like a normal QPSK constellation, noisy one. You can see 4 constellation points. The first one is the constellation diagram that you see when there is a frequency offset, there is a phase offset, and you can see that when we have restored this frequency and phase offset, we are getting only 5 bits in error out of 1000, whereas when we are not restoring, there are 43 bits in error. Ideally, if I did not have put this carrier offset or these things, then at 10 dB EB by N naught for QPSK, the bit error for would have been 0. because we have sent only 1000 bits, and the errors will get visible because bit error is of the order of 10 to the power minus 5. Once we transmit more than 10 to the power 5 bits, then only we'll get one error maybe. I can do it for longer, but it will take some time. What I wanted to show is that this type of restoration circuitry, which actually synchronizer, carrier synchronizer do work, and these are based on PLL, and they can effectively compensate for the phase and frequency error these are produced. Now, this is again a simulation block level. In actual practice, it has to come to the hardware. And as you know that nowadays, we do not make these things from discrete hardware. The signal processing takes place at the digital platform itself in the baseband, either in some DSP or so. So these are implementable also in practice. I change the EB by N naught ratio from 10 to same. I make it very poor now, say 4. And I rerun this. And now you can see, even after restoration also, you are not able to see the deep, you are not able to see the clustering because the noise is very high. It keeps things spreading, and we get some better performance here. Now 140 bits in error, and here when we do not do any compensation, 196. So SNR or the noise level also plays a role on the performance of this type of circuits, because whatever we discussed in our discussion, we did not consider the noise, so it also has to be taken into account. Another scheme that I'm going to discuss again on the level of block diagram is the early late gate synchronizer. And we said that this type of synchronizers are used for synchronizing the or rather deciding the timing when to do the sample, for example, at the output of the demodulator. And this had your symbol duration, there was no delay or there was no variation in the time. Once you decide, it would have been done, but you require to continuously update this, because in practical system, as we said that this keeps on changing, the delays and these things may not be fixed. If it is a fixed known delay, you can make it for once, but you can also address when the delay is not fixed, it keeps on changing. So the idea is something like this. If you have a ST is the symbol, it is a rectangular symbol you are transmitting, it has a duration T, and at the mesh filter, when you actually perform convolution, it is from 0 to 2T, and the peak of this occurs at T. These are ideal scenarios. Now, the output of the filter mesh to ST attains its maximum, the correlation T equal to capital T. time to sample the output as the match filter for a maximum output is actually at capital T. That is at the peak of the correlation function. But what happens in the presence of noise? Identification of the peak value of the signal is generally very difficult. So the strategy that is adopted, instead of sampling the signal at the peak, suppose we sample at an early time t minus delta or at a late time t plus delta, because we do not know exactly when this is occurring. So we sample little early or we little later. We have uncertainty about peak is occurring. We under peak occur within a noted by delta, and our autocorrelation function is even with respect to the optimum sampling time. So it is even function, and therefore what you expect, that magnitude of y of m t minus will that of t plus delta, and under this condition the proper sampling time is the midpoint of these two, t plus t minus t minus delta to t plus delta, and this condition forms the basis of the early late gate symbol synchronizer. So we do not know exactly when this peak is occurring, but we approximately know where it occurs, and we exactly do not know because of the noise. So we sample a little early, we sample a little later, and then the midpoint, the average, will possibly will give us the time where it has to be sampled. And this is actually realized in the form of a synchronizer circuit. I will discuss only at the block level. So here you can see you have a symbol waveform generator, and here you have a voltage control clock. This waveform generator generates the waveform ST advanced by delta and delayed by delta, and now the received signal, here you can see that it is correlated with a change in delta timing, either advanced or delayed, and then this magnitude is taken, and these magnitudes are actually compared here, and the error signal generated is given to a loop filter which controls the VCC, the voltage control clock generator, and from here you can also extract the symbol timing. So this type of synchronizers are very simple to understand and is popular also. There are many other forms, the synchronizers, for example, MMAC, maximum likelihood, and other forms of synchronizers are there. And if you want to really go into the details of the in PROC is digital communication, book, a full chapter is dedicated to synchronization and career recovery. I've just discussed the very preliminary things so that you get an idea why these things are important in the practical communication systems, particularly digital communication systems. So I think we are already come to the end of our allotted time, and I stop sharing, and I can take up if there is any question which is posted, or if somebody wants to ask anything, we can take it up. Pubali, any question? Firuza, any question? Can you hear me, Pubali or Firuza? Saboshachi, can you hear me?
Sir, I can hear you. I can hear you, sir.
But then there must be some problem with our E&ICT Academy. Their mics are muted, I could see.
Yes, sir. Their mics are muted. I am getting in touch with them and just trying to resolve it out. Just a second, sir. Sir, sir, their internet got disrupted, so they are trying to reconnect within a while. Sir, just mentioned me to pass the information.
Okay.
To you.
Do you have access to this question answer, this panel? Any question
Yes, sir.
answer?
I'm trying to get that. I'm trying to get that.
If any question answer is a question is there, then I will try to answer.
Yes, sir. I'm just checking that.
Or today it is already 1:40. I think people must be feeling hungry also.
Yes, sir. Yes, sir.
So let them recover. Tomorrow I have got a session.
Yes, sir. Yes, sir.
So if any queries are there which could not be discussed this session, we can do it in the next session. Okay.
Yes, sir. Okay, okay, sir.
Okay. So I'm actually now disconnecting myself. Huh?
Yes. So on behalf of
Oh. Um, Actually, now I am the host. If I leave, then the event will end. So what should I do?
sir, that is what they have just mentioned to within a while they are trying to get connected, sir. The Firoza
Okay.
ma'am already connected, I guess.
Just Firoza could yeah, Firoza.
Firoza ma'am, am I audible to you?
Let me call her over phone and let me ask what
Sir,
I am supposed
sir,
to do.
yes, sir.
Okay, Shabashachi, I am leaving the event. I could get that option. Huh? So it will. Hello, Shabashachi. Hello. Hello, Shabashachi.
Yes, sir. Yes, sir. Actually,
So I am leaving the event. The event will be on. Huh? I have got
yes,
that option.
okay, sir. Okay. Thank you. Sir, thank you for the talk. Thank you for the talk. Thank you so much. Thank you.
Hello.
Yes, sir.
Hello.
Yes, sir.
Oh, I'm still on, but I have given leave event. Oh, select a new host. I will have to select a new host. Then only I will have to. I'll. So.
Sir, that host should be among the panelists, I think.
Yes. So I'm putting you as the host, and I'm
yes,
leaving.
sir.
Huh?
Okay, sir. Okay. Thank you, sir. Yeah, Puvali ma'am. Yeah, sir has put me as the host, and he has left the he has left the platform. Yes. So what should I do? Good afternoon, Firoza ma'am.
Yeah.
This is Sabyasachi.
sorry, we suddenly had some breakdown. As a result,
Okay,
we
madam.
were not able to run.
Yes, it is okay,
Please,
madam.
for
Just
the
that
thought.
sir has, Professor Bhattacharjee sir has actually left the platform. He has made me the host. So currently I am the host. So please guide me on what I should do.
Please, sure. Thank you. Really sorry for this. Suddenly we had some issue with the network, so we weren't able to reply to the query. We are really sorry on behalf of our academy. Yeah, thank you. All you papers will correct by 9:30 a.m. please. Thank you.
Firoza ma'am, what should I do? Like I should end the event?
No, I'm doing. I will be
You will be
doing. I
doing it.
request you also please leave the meeting. We will be ending the meeting in another 5 minutes.
Ma'am, could you just repeat? Could you just repeat what you said? Actually, your voice is breaking.
Told that now I may request all the participants to just leave the meeting. We will end this event in another 5 minutes. So you all may disconnect now.
Okay, okay. So the participants should leave now, and again they will get added.
Yeah.
Yeah.
Okay.
Okay.